Just a quick hello. Hi, everyone. My name is Deborah Isaac, founder of Houdini School. Super happy to have Dave here today to continue on with his incredible Forces lecture, Forces 2.0. So with that, I'll let you take over, Dave.
Awesome. Thank you, Deb. Well, welcome to everybody here. I am so grateful that you all showed up. I do apologize for the 2-week delay. Things got quite chaotic over the holidays there and got sick, and I'm doing much better now. I do have a lingering cough, so I apologize if I kind of toss my head to the side every so often if it shows up, trying to avoid blowing out your ears with a loud cough. So let's see here. I'm going to start with just a quick introduction of myself. For those, hopefully most of you are familiar with me if you've seen the first Velocity Forces class, but for those who don't, who haven't met me or anything, my name is David Torno. I am a former visual effects veteran. I worked for about 20 plus years. I worked on features, I worked on music videos, animations, a variety of different topics and everything. I was primarily a compositor, and for 8 years of that timeline, I was a technical director. I freelanced the other years that outside of the 8, I worked for a company at that point. I primarily focused on volumetrics and particles towards the end of that part of the career before hopping over into just focus on teaching full time. It was always there. I've been teaching since 2008. But more like on the side and through video tutorials and stuff. But here I am teaching live now with Deb and Houdini.school. Let me share my screen here real quick, just to kind of continue the conversation over here. And let me move these thumbnails out of the way here. And let me go to, where's my window? Not that one. There we go. So, and there it goes. One thing I want to point out, since I do teaching in the live fashion, but I also do one-on-one tutoring as well. My personal website is fendereffects.com. This is kind of like the encompassing of my entire life's work. So going back to the old school days, I've got all my After Effects tutorials, Cinema 4D, some very old Redshift stuff, Turbulence FD, training series, and a lot of utility scripts, both for Houdini, After Effects, and Cinema. I've been doing coding stuff for a long time, as well as X-Particle stuff. As of the last, I would say 5-6 years, roughly, I've been dedicated to Houdini straight out. That is kind of the one and only app that I'm using across the board. I kind of dabble with this more to maintain some old products that I made, but I don't really use any of the other softwares for the most part anymore actively. But if you want to learn more about me or look at any of my old stuff, this is the place to go. I have a tutoring link over here too, if you ever want to do a one-on-one through Zoom. So it is global, and it is, whatever you want to talk about Houdini wise. My knowledge is vast, but also limited at the same time. I do preference Vex because that's kind of what I know the most, but I definitely branch out and assist with projects if you're trying to troubleshoot something or just want to talk Houdini. For today, before we dive into starting any part of the class, I want to make sure you have a lot of the assets. Excuse me. So there is, and I'll put this in the chat here because this was a last minute upload, which is the project file. I'm gonna put this in the chat here and I'll just mark it so it stands out. Just say project file if I can type correctly here. So that link you're seeing in there is a Google Drive link. That is the actual project file that I will be using today. If I was to change anything during the live class, I'll also upload that as well afterwards. But you should be able to find this on the account, your Houdini.school account. If you go to the Velocity Forces 2.0 class and just go to the resources where it says files, and you'll see downloads. And inside there, you're going to see a couple of things that I've kind of put up there. There's some useful URL links to some information, as well as another training series that I'm going to kind of plug a little bit by another individual, Peter Clace, who's a Houdini veteran as well as some of these other documentations that will kind of go over throughout the course in general. And then the actual downloads themselves, there is an HDA that's in there that I made. It's open source. It's just the FFX polyline arrow. It's for a visualizer, so it's not anything that's for effects or anything, but this is for a visualizer. I tend to make my presentations in Houdini, and this is part of that presentation. So if you want to follow along with the project file, you can download this HDA as well. This is a PDF that I'm going to go over here shortly to show what we're going to be talking about today. There is also a shelf tool Python code here that we're also going to be talking about in a moment. And this is to help fix a bug that's currently in Houdini, of which I filed a bug report for already. But until then, this is going to mitigate us having to do a lot of things manually. This will take care of it for us. And the last one is the zip file, which is the project file as well. So if you already grabbed it from there, that's great. Otherwise, check the chat window for the current link from the G drive. So with that, let's hop over to the outline. The kind of overview that we're going to go over today, this is the PDF that I just mentioned. For session one, before we begin, we're going to be taking care of this shelf tool because this is also part of my presentation stuff. So the font node apparently has this weird bug where it just won't cook correctly when you first open the project file. So the font strings, all of the text that I have, it just won't update as I change things. And this will actually correct that. It basically is a script that will find all of the font nodes, turn them off, and turn them back on. In doing that, that somehow forces the node to cook and fixes the issue. So we're going to automate that. All you're going to do is copy and paste in this regard, so you don't have to worry about memorizing the code or anything. Once we finally get that going, the volume definitions is going to be the first section we're going to be talking about. And this is basically the volume primitives that are available in Houdini. We're going to be going over two types of primitives, the Houdini standard volumes and VDB, also known as OpenVDB. We just call it VDB for short. We'll be talking about the field data types that these can house, these two types of volumes. We also will be talking about the terminology here of volume and field. I'm going to be sticking to volume for kind of like the first part, and then we're going to be migrating to the term field just because of how it relates to simulations. And I just want to kind of ingrain that terminology in your head. A lot of people use them interchangeably, but it kind of is associated to simulation versus geometry and so forth. It's these little nuances of the terminology. So we're going to be going over scalar fields, vector fields, and signed distance fields, also known as SDF. And then these yellow ones are just kind of like some subtopics that we'll be kind of highlighting and going over. We're going to be talking about the VDB tree structure. This is kind of a behind the scenes structure of VDB. And it's important to understand this, and mostly because of how it can affect things on the front end. There are some possibilities of glitching that you can encounter, and this is related to how the structure of this works. So we're going to be talking about different aspects of that. We're going to talk about field creation and subtleties. So I'm just going to show you a couple of varieties of how to create scalar fields and how to create vector fields. There's a couple of different setups. In the first class, the first velocity forces, we talked about volumes, we talked about vector fields and voxels and so forth. We're kind of building upon all of that knowledge. So some of this will be familiar, some of this will be continuation of what we kind of touched on in that first original class. It's listed as a prerequisite for this class, but don't feel like you're going to be lost if you did not watch that first class. We are going to kind of like reiterate a few pieces here and there, but excuse me, tap my microphone there. Let me reposition that. But we will actually be kind of continuing that and building upon it and talking about some more advanced aspects of a lot of that stuff. So we're going to kind of like take this to the next level, essentially. We're going to be talking about field masking. So this is how we're going to take one field and use it as a mask for another field. And we're going to talk about a couple of different simple mathematical equations of add, subtract, and multiply, and some of the actual nuances of what to watch out for and how to optimize based on these structures that we're going to be talking about. We're going to be talking about velocity field glitches. I was just mentioning that, and this relating to VDB, where you get these popping and weird kind of glitches as you activate velocity fields sometimes, depending on the type of effect that you're applying it to or how you do advection. We're going to be talking about why it's doing it and some solutions to kind of mitigate it. We're going to talk about masking via the camera frustum, so how we can actually do masking via the camera itself. And a couple of tips on showing the frustum itself. Velocity fields from sims. We're going to also focus on kind of continuing again from that first class with using velocity fields that we're not building from scratch per se, strictly the velocity field, but we are using a simulation to generate a velocity field that we then use to do our advection and so forth. So a couple examples for Pyro driving stuff and for a Vellum Sim driving stuff. So we're going to use a variety of different kind of setups. We're going to be doing a threads advected kind of simulation. And we're going to go over a lot of the different kind of keynotes like VDB analysis and VDB merge, our good old friend, the pop advect by volumes. This is the most common one, volume rasterized attributes, and setting a few other things here and there. So this is the general overview on that. Let me check my notes real quick here, make sure I've touched on all my topics. Pretty much, yeah, we've pretty much hit all of those. One thing to note is if you are not super versed with attributes, they are a key part of Houdini in general overall. But when you're dealing with customizing your simulations and dealing with all of these velocity kind of setups and whatnot, attributes are inherently going to be a part of it at some point. So if you ever wanted to deep dive and just get a really solid understanding of that, I also have a class here at Houdini.school for attributes, if you want to check that out. All the other ones are pretty much, you're already in this class, you don't need to sign up for it. And this is the first class. If you didn't check it out, I would highly recommend that you check that out because it will make understanding some more advanced techniques a little easier to kind of digest. These other ones are going to be ones we talk about a little bit later. They're just quick links to actual information that is going to relate to what we're going to talk about. So let's hop into Houdini real quick and talk about some setup stuff before we get into the nitty-gritty of all of this fun stuff here. First things first, the HDA. To install that, just download that zip file, unzip it, save it wherever you want to save it, and then just go up to this assets, install asset library, and then you'll see this digital asset library. Just click this little icon right here, find that HDA file, select it, hit accept. Once that comes in, just this install right here, you want to make sure this is scanned asset library directories. Once that's flipped over and you have it selected, then hit install and you should be good to go. At that point, you can load up the HDA. So that should mitigate the errors if you didn't have it installed when you open the project file. So that's the HDA. The other being the shelf tool. So for any one of these shelf tools, or shelves, I should say, up here, these are the stock ones. These are some custom ones that I've made for myself to organize my development and for my tool sets and whatnot. You can create those by hitting this little drop-down arrow. It's really hidden, but you can just say new shelf set, and then you just fill out the name and give it a title, and it'll pop a new blank shelf. And you can place that in one of the other ones, or you can keep it separate, however you want to combine those. But what you want to do, and this is kind of a key thing, anytime you create a new shelf or you create a new tool on that shelf or any shelf for that matter, you want to make sure that you use this save shelf set as. When you do this, that will save all of those creations, the shelf tools, and so forth. I usually give mine just, like a personal ID of some kind, just my initials or something, and just say all my tools or whatever's relevant to the name. And that's going to encompass all of my stuff that's in the shelf total. One thing I've run into that's not super apparent is when you make changes or add new tools and you don't save, it's not going to go to the file. And if you try to migrate, and I found this out the hard way, I went from 19.5 to 20 and I migrated my file and realized I had saved it at one point, but not after I had added 12 or 13 other tools, and none of them showed up. So you want to make sure every time you make a change up here that you just save that shelf set as, and just save over the file that you created each time. And that'll actually update all of the information and make sure that you have that file. So to create a new tool, just right click within the shelf itself and say new tool. And for this one, I'm going to edit my existing one just to kind of show you. This is the tool we're actually going to use. For me, I just called the name Fix Font Nodes. I try to be kind of literal with that. This is the behind the scenes name. So it's very similar to like parameters. When you hover over these things and you see the parameter TX, TY, TZ, that behind the scenes name, that's essentially what this is. The label is just going to be the name that you see up top here. That's the one you actually will see when you click on the button. I just called mine Fix Font Nodes. Icon, you can leave it by default. You'll just get that little H like that. If you want, you can click this button and choose from any of the stock icons or choose your own. I just have some generic ones, which are numbers that I use, and those are just put into there. So the important part is the script itself. So I'm going to open this up a little further. So go to the script tab. It'll be empty at first. And the file resources that I uploaded there should be a TXT file, and it has all of this text. The only difference that you may see here is that I have a comment for a debug section. You don't have to worry about having that. It's not important. It was just for my own use. So this code, all you need to do is just select it all, copy it, come in here, paste it, and then you should be good to go. Hit apply, accept, and then you'll have a button up top that you can just click and have things get fixed. Just as a brief overview, we're not going to dive deep into the code, but this basically is looking for the current pane and specifically the network editor pane. So it's just grabbing that information. And then down here is just checking to make sure that we are actually on the network editor pane and finding it. If it can't find it, then the code just terminates. If it does find it, then it just creates an undo group. And then it's going to loop through all of the nodes in that actual pane. And it's going to look for a specific font node. So it's just looking for the type of it. And then it's going to do that process of turning off the bypass and turning it on. I'm going to hit cancel out of that, and just that would be basically, you should all be familiar with this at this point, but I'll just point it out. The yellow here, when you turn off a node, that's bypassing and turning it back on. That's essentially what this script does. It just turns it off and turns it back on, forces the node to cook, and fixes the issue that we run into. Any questions on this before I move forward? Cool. So I might cancel out of that because I already built it. And I think that covers us for the setup stuff. Pardon me. So I'm really organized, as you can see. So you're going to see a lot of network boxes, and you're going to see a lot of color coding and so forth. Just a general note overall, if you see yellow text, those are usually just highlighted notes of information or a tip or something along those lines. Definitely keep an eye out for those throughout the project file. We are actually going to be starting on this one, 1.0 volume definitions. And we're going to dive inside here. Let me hit H real quick just to kind of show this overview before we get into the actual nitty-gritty of information here. I have controller nulls, this little circular null right here that says C on it. I'm going to be using those for my presentation. You don't necessarily have to. I just want to point it out because I'm going to split my parameter pane over here with Alt right bracket. And that's just the square bracket that looks like that. And that splits my pane vertically. And then I'm just going to pin this so I can have this always up and available. I'm going to put it at the bottom here to kind of keep it out of the way. So that way, as I select stuff, you'll see the parameters show up kind of more naturally to your eye straight across here. And hopefully this will be out of your line of sight. This is primarily for me, just so as I go through, we can see our text and so forth. So speaking of text, since we are now in this area, as long as you've got your shelf tool set up, just click this button and that should be good to go. So now as I switch through, I should see all of my text change accordingly, which it looks like that's updating. So we should be good. If it sticks at any point, we can always re-click it during that moment. So general overview of what's happening here is I have some source geometry. Don't be too concerned about how things are built here. That's not the point of this here. This is primarily more of a presentation aspect. You're going to see a lot of gray nodes. Those are basically uninteresting. Don't worry about it. Don't think too much about it. It's the yellow nodes that I will be talking about. Those are kind of like the more important information bits. But in this particular area that we're going to be talking about, they're not super important because I am going to go into actual detail talking about how to build scalar and vector fields. So these are just more highlighted because I'm going to point out a few things as we go through. So this is all going to be about Houdini standard volume. This is going to be OpenVDB, and then I have a few others here. The VDB structure, and this is actually SDF, which I forgot to label. So I'll save that in there and I'll re-upload that file as part of one of the new live class files. This on the side is just going to be related to when I talk about something over here. So not super important until I get to it. So with that, let's actually start the class after 20 minutes of trying to get everything set up. So we're going to start with volumes overview. In general, we talked about, creating volumes and fields in the previous class. We talked about the voxels and so forth. This is going to be a better kind of continuation and structured version of the specifics of these, because understanding that's going to help take you to the next level of kind of controlling things. So I've got the link here. This is the link to the help docs directly that I've basically copy and pasted from. So the volumes overview. So volumes are basically, they allow you to store values for voxels, three-dimensional pixels. I personally don't like the term pixels, but it is probably the easiest way to describe a voxel, being that, pixels are 2D, it's X and Y for the most part, and voxels obviously are 3D because we have a Z component. So this allows for storing voxels in a space. What it means by space is this, world space. This entire area is what we can fill with voxels, basically. This allows you to represent phenomena such as cloud, smoke, fire, store simulation metadata such as velocity fields. So it's basically a velocity at each voxel. We should already know this. We talked about it in the first class. And use velocity values to move, or what's known as advect or advection. Again, should already know this. Basically moving other geometry. We can create collision fields, which is storing 3D hittable areas of an object as a signed distance field. This is one primary form of collision to use as signed distance fields, or SDFs. You can do it with volumes as well, but primarily SDF works best because of some features that it has. The Houdini overall supports two types of volume primitive. I want to point out primitive, and I talked about this in the attributes class. If you happen to have seen that, primitive is a horrible term to be used, and they even admit it in the docs themselves. It is kind of a generic term that's been used for a lot of different things. We're talking about sphere primitives, torus primitives, volume primitives, pack primitives. It gets used so many times, and primitive also being a polygon face, that it gets very confusing really quick. But the overall syntax of this being that volume primitive is what they're going to refer to it, they being Houdini. This is basically at the geometry level, which is where we're at right now. This is SOPs. Should already know this, that we're at object level. You put down a geometry node, you're now in geometry SOPs. Get my place again. So the two different types are basically adapted for different uses, but Houdini does try to basically work with them generically where possible. So they kind of are interchangeable, sort of. Not 100%. There are some caveats and quirks. So we're going to start with demo 1. If you are following along, it's going to be demo 1 in this, or 0, excuse me. All right, we start at 0, just to maintain the 0-based array kind of system. But we're going to start with Houdini standard volume. So that's what we're looking at right here. I'm going to hit 3 to go to a kind of perspective or a side view here. Turn off my grid just so this is kind of readable, and give us a little more space so it's a little larger. So this is a good old standard Houdini volume. This is their proprietary native solution that they've programmed in here and is basically throughout the entire app. So Houdini standard volume is a box with a position, size, and orientation subdivided into a 3D grid of voxels. That is sounding pretty straightforward. Temporarily, I'm going to go perspective here. What it's meaning by the subdivided into 3D grid of voxel, this box, it's usually referred as a domain. So this domain is what's going to contain all of this information of voxel information, and the voxels being all of these. So what we're looking at is every single individual voxel based on a 0.1 voxel scale. And what you're seeing there in the red is the active voxels. Basically, they have values. So that is where we're seeing the fog field that's happening right there. So these voxels, basically, they store, a value at each of these voxels. So this type is used in modeling for SOPs and simulation and DOPS. That's kind of a limited kind of definition there. They kind of do a lot more than that beyond modeling. But this is kind of like the baseline of what they're kind of using these for. The different types of volumes are storing different types of information in the voxels. This is where we get into scalar and sign distance fields and vector fields. So let me turn this back off real quick and just kind of show this. You may see as I'm moving around, let's go from blocky to fuzzy. This is a OpenGL viewport thing, just in how it displays. So don't worry about it like you're losing information or something. A lot of that has to do, if you hit D and go to, I think it's texture, 3D textures, you can limit the resolution of what displays here. I usually try to keep it at like 512 or 256. 256 is the default. But if you have a high resolution field, the resolution here will limit it. So you may have high resolution, but it won't display it. So you want to kind of be aware of that and be careful. You can always take that number up, but you don't want to keep it at the high number because it does get heavy to navigate. So we'll start with the first type here. And this is a scalar field. Most commonly density. And one of the other things, I'm going to pull really quick before I move forward. Let me grab this, and I'm going to pull it to the side so I have access to it. It's kind of my overview notes there as well. So it's doubling for a few things. Let's minimize that. So for the scalar fields, this is basically a float field. So you're dealing with a single, fractional value, say 1.529, blah, blah, blah. So that's just a single float value. You're going to see scalar and float kind of interchangeably throughout some of the documentation and also within this presentation. But just know that that's basically what we're referring to is a float value. It's meant to store a single numeric value at each point. Bad choice of terminology. I would prefer that said voxel because that's what it is. But the voxels themselves have basically a center point. If I go back to the 3 here, we can see that what it's referring to is basically this point location, essentially the centroid of where the voxel is located. It's a positional value. So that's where the value technically is stored. So this is useful to represent, again, smoke and a variety of other setups. Density being the most common one. Some of the other ones is like temperature, and there's flame. Let me move my other window out of the way here real quick. So temperature, flame, burn, and mask are some of the other kind of common ones that you'll see in there. For SDF, I'm kind of briefly go over this because I have a dedicated SDF visual to kind of go over on that. But what SDF is, it's used to represent fluids, is what they say. Again, this kind of represents so much more than fluids personally, given that we can do colliders and so forth. And I'll turn that off. So if there was a geometry, in this case, we're dealing with the field, but the geometry itself of Flippy, we'll say, looks like this. It's not the greatest Flippy drawing, but we get the idea. SDF, in short, basically has a boundary of voxels on the exterior and on the interior. And it's basically a definition of the surface. We're basically getting a value that's defining where that surface is what this is primarily for. So it stores a number at each point representing the distance to the surface of that geometry. It is most commonly used in fluids, which is why it's saying that. With the sign of the number, positive or negative. So we're getting negative values on the inside, positive values on the outside. They show an example here. Oh, sorry, I'm jumping ahead. The sign distance field, so it's indicating whether the point is inside or outside, basically, for SDF. Vector field, we should be familiar with this from the first class. We're storing a vector value at each voxel. So that is something that's pointed out in here, that this is actually represented using a 3 scalar fields. Now, what is that actually meaning? The example they have in here is cd.r, cd.g, cd.b. Well, we already know that, a float would be a single value, whereas a vector is 3 values, usually x, y, and z, or r, g, and b. So we end up with this kind of collection of values. Now, it's saying that it's doing 3 scalar fields. And I'll undo these just because I'm going to move this. And as a really quick example, don't worry too much about anything that's set up on here per se. It's more just to illustrate this scalar split that's happening. With a standard volume, it's just a Houdini volume. It's known as volume there. If you hit tab and go to volume, these are all of the Houdini standard volume nodes. And above is VDB. These are pretty much labeled VDB. They all pretty much have the same icon except for the one. So these are pretty straightforward. They also have the VDB prefix at the beginning of each of the names. So they should be easy to kind of spot between the two. There is also a color scheme, as you may notice here, that there's kind of a greenish and kind of like a purple bluish, which is also occurring in my net box on the standard volume. And when we get to it, the VDB as well. I'm trying to associate everything here because you need to get familiar with some of those differences. When I middle click on the Houdini standard volume, this is the 3 scalar fields that it's referring to. This is a velocity field, and we're getting X, Y, and Z as independent fields, and they're float fields. There's roughly 1,000 voxels in each of these fields. So that is what this is referring to. So Houdini standard volumes will only be split like this for vector. Each one is independent. Whereas with VDB, you'll get a single one. And a key thing to note between that is that these are 3 float, and this VDB setup is actually a vector. It's a vector 3, and I think S being scalar as the subtext on that they're packaged together essentially. That's one of the benefits of VDB, but we'll get more to that when we get to VDB. So that's a key difference to note. The other being that color. So we can see that these are kind of green colored, and this is kind of like that bluish purple color. So if you're ever building something, and most nodes will kind of define that they want a VDB specifically, especially if you're using any VDB node, you're going to need a VDB input. So if a standard volume comes into this, it'll probably give you an error. And if you don't have that coloring, available, and you're like checking through attributes, pay attention to the colors. That will be your first clue right there. And then with any vector ones, you'll see that as well, that split that happens. So a common use for this type of field, obviously, is a velocity field. For gas simulation, you'll see the term gas a lot as well. There are gas nodes within DOPS. And we don't really go over any of those in this particular class because those get really, really advanced. That's basically if you're building your own solver from scratch for the most part. You're doing micro solvers and kind of stacking a lot of these. There's a few of these that you can actually pin in there as kind of auxiliary dissipation, and I forget some of the other ones. There's vorticals as well. I do have a vortical example actually that we'll show in the later sessions. This basically represents the point's vector value, which represents the direction and velocity. Again, going back to the first class, we had the voxels and we had those directional vectors. So each voxel had a direction, and each of those have a direction that also has a magnitude. So if that magnitude, the length of that vector was greater, it's a stronger force that's happening on the velocity that's coming across there. So that's what it means by direction and velocity itself. We did talk about in that first class as well, magnitude. That was a key part of it, and that's just the length of the vector. One of the other notes they have in here is that you can use VDB vector merge node to combine 3 scalar VDB fields into a single vector VDB. That is true. Why this is in the Houdini standard volume, and let me take my thing off there. There we go. I don't know why that was in this section. That's pretty much unrelated. If you try to combine these 3, which is a standard volume, using the vector merge, it'll fail because it's a VDB node and it requires VDBs, which means you would have to convert these to VDB first before it would recognize it. So this, I feel, is in the wrong location personally in the docs. That should be over in the VDB section of it. So for the Houdini standard volume, the basic, really, really basic setup is feeding your geometry. So this default geometry, it's just flippy, nothing fancy going on there. It's just test the rubber toy, and I cleaned up the attributes, booled it to make it one single object, and then did a match size to put it in the center of the world. That is just object merged and coming in here. So we're just feeding that geometry into this volume. I'm going to hit this activate thing. This is a quick button. If you want to know what that's doing, and I'll explain the code to you like after class or something, it's basically finding my output so I can easily hop back to it if I end up activating any of these nodes to show you stuff. It's just a convenience thing for myself, but I'm happy to show you the code at any point later. So ISO offset. If I hit tab, go to volume, and ISO offset is right up top here. That is like the equivalent of basically the VDB from polygons that you're probably more familiar with. This is the Houdini standard volume version of this. This was the original way to kind of make volumes. You basically can make a fog volume. You do have options for other setups in here. The mode in which it makes it, and the name. So by default, I'm just making it a density volume in this particular case and giving it a division size. This is expression only to my master controller, so I can actually do this globally and change the values, but you can just set the division size. So that is the basic kind of setup for that. If I hit the domain again, this is the actual bounds of that domain, and we can see the relationship. I want you to kind of pay attention to some of these subtleties that are happening. One being a little bit of a fall off. You know, it looks brighter here than it does here, and that has to do with the overall transparency of the value here and here being stacked up, essentially. But we have this container, this domain that is having all of these voxels, some active, some inactive. And when I display the voxels, we see the actual voxels that are there that occupy that. So even if they're empty, we do still have voxels there. They are being saved to disk. They are being saved to memory. They have to be processed. They exist. They're all activated. If you middle click over this, you get a general idea of what the memory setup is on that. They have, SideEffects has optimized their native volumes obviously very well. So memory-wise, you may find pros and cons as far as it being a little better memory-wise sometimes than the VDB, but the VDB efficiency stuff that we'll show detailed in a moment makes up for some of that and actually takes it a little in a better direction for efficiency. for storage and space and all of that. So we can see that in this entire domain, we have 11,088 voxels. There's a resolution of 24 by 21 by 22. If you middle click, you'll see these same numbers. This is the actual grid res, and there's the voxel count right there. So the grid res is just basically X, Y, and Z. That's how many voxels are going in all of those directions. The domain you will hear referred to as grid. Tendency of when you hear the terms grid and domain, the assumption, mostly for myself at least, is that you are getting voxels in the entire space. Like it's what's called a dense grid. Dense being another term, because we're going to talk about an alternative term that's for VDB known as sparse, but dense being that everything's going to be packed in there. So every little spot has a voxel, and that adds overhead at some point down the line. So the next section here, I want to just double check, make sure I didn't skip any specific thing here. Yep, looks like we're good. Before I move over to VDB, is there any question on just this general Houdini standard volume?
I think we're good.
Awesome. So let's hop over to OpenVDB. And I'm going to turn this off for a second. I'll keep the domain up because I'll reference that. And hopefully this changes. Yep, cool. And we're on that. Pardon me. Okay, so demo one is the OpenVDB volume. So one thing I want to note, I'm going to go to 3 on my keyboard to get this perspective view here for front. And I want to toggle back and forth between the demos, the standard and the VDB. And we can see some differences here that are occurring. And I want to make sure I'm on my main output just in case. Cool. So we're seeing some clipping is what it kind of looks like. We see the domain is out here. And if I go to this one and I'll turn the domain on this one, we'll see the difference between those. It kind of clips inward like that. If I show the voxels, I'll turn the domain off briefly here and show the voxels, we'll see some key differences. This is VDB. This is the Houdini standard volume. VDB obviously has way less voxels, and we can see that in the number right there, 1,218 with the same resolution, 0.1 in this case. So that is one of the first things to kind of pay attention to for the efficiency part of it. So an OpenVDB volume uses the OpenVDB library. This is a third-party open source kind of thing. So this is, I don't want to call it an afterthought, but this is something that was imported in and kind of tacked onto Houdini. It's integrated, but it's not overriding at the core level, basically. So this is representing a sparse volume. And that's what we mean by dense versus sparse. Sparse because there's just less. There's not as many voxels in there. It's basically only using the voxels that we need. Anything that's active in there. So if I toggle that back and forth, we can see that that's the actual volume and that's the voxel. So we only use what we need, which is great. So the VDB volume uses essentially no memory for those empty voxels. Now, technically that it does have to, the voxels themselves equal to a background value. If I select one of these to kind of reference, I'll pull up this one. I think it shows, and of course it doesn't. It's in one of my other ones, I think, over here. There it is. So when it's talking about a background value, it's basically this kind of default. If there's no active voxels, there's this background value that happens. And you can set that to whatever value you want. So it's kind of like this fallback, essentially. So this volume type is useful for modeling sparse volumes such as clouds and wispy smoke. Pretty much the same kind of stuff. You can use it for modeling as well because you can convert these volumes into geometry with a few helpful nodes that are in Houdini. Because of the way this volume type is represented in memory, it does not require that you specify a box containing the volume. So this concept of a domain is just more of a boundary, and it's just a boundary based on the voxels that are there. So if I go back to perspective, we can see that all sides of this are pretty much up against the voxels, front, back, and so forth. Whereas on the standard volumes, and let's do that, you have a buffer zone. So if I go to 3, the color doesn't want to show, of course. So where the red is where the active voxels are. You can see that there's still this kind of buffer. There's another voxel that's kind of there. There's one that's kind of 1 or 2 that's above this one, and one in front of that. So there's a different kind of algorithm running that. So we can see how that kind of pushes everything in. So that's great from an efficiency standpoint. So you don't have to define a domain and say, okay, you're going to stay within this. Being that it is this open kind of space setup, it can extend indefinitely. So that means you can keep going and going within your entire world, the world space here. Come on, there we go. Pretty much it'll just keep adding and adding more voxels however you want within the limits of your machine and memory and so forth. But despite that, the VDB does define a 3D grid of voxels over that space. And what that means is basically this can go infinitely, but these voxels will not be offset in any kind of bizarre way. If I was to put, one at an angle here, and then we'll say another active here, it would kind of line up like that, but it's not going to go in between, or it's not going to be, rotated at an odd angle. If we had a voxel going this way to encompass an odd corner or whatnot, it's still going to be this grid formation that's happening right here. So the same as what you would see with a standard volume. So it just infinitely kind of stacks them out further and further and further. So let's see here. So OpenVDB, it was added in 12.5, so it's been there for a while. You can write OpenVDB volumes to BGO files. This works in Houdini specifically because you can load them at render time using mantra delayed load procedural. Obviously, we have Karma now. I don't know with the gold version, I haven't been able to test this yet, if Karma has officially added the same load for that. If it can do the VDB as BGO, I'm pretty sure it could, but don't quote me on it just because I haven't actively tested that quite yet. But you can save them to these BGO files. Now, if you're going to export a VDB out to another DCC, which is very common, if you're sending this off to Maya or Cinema or some other app, you can't use the BGO unless that app specifically has programmed it to read that data format, which is pretty much Houdini specific. You need to save these as .vdbs. And that's the universal extension for that. And it's pretty straightforward, but it's just .vdb. So you can render standard Houdini volumes and OpenVDB together. They will mix properly. Even though that's the case, I tend to try to make sure everything is uniform, or unified would be a better term, and just to eliminate any possible debugging of, is this one broke or is this one broke kind of a thing. At least I know I'm all in one kind of space. There may be the case where you need both. I personally haven't come across that, but I'm sure there's some edge case out there that would require that. So surface nodes, SOPs with VDB in their title, which I showed earlier. Get that up. There we go. So all of these with VDB at the prefix. Pardon me. So those in their title, they operate on VDB volumes specifically. You can convert geometry to VDB volumes using the VDB from polygons and VDB from particles node. They're pretty much the same, just one's engineered for particles and the other one's meant for polygon shapes. You can create an empty VDB volume using the VDB node. This is basically what we're going to show right here. There's a kind of variety of setups that you can use to create these VDBs. And you can create an empty VDB using the VDB node. Other VDB nodes let you edit VDB volumes. So many SOPs that operate on Houdini standard volumes also work with VDB volumes. So the node will help indicate if the volume node doesn't work with that. It usually will give you an error or tell you if something is not compatible. That's basically when you select this and you hit the help doc, the little question mark. This will take you straight to the node. And usually in the first couple of sentences or a note towards the top, we'll say whether or not it works, with one thing or another. This usually, there it goes, zooms in. So just kind of skim through the upper portion of the help, and that'll give you a idea if there's a limitation for that. There are VEX functions, Python, HOM, the Houdini object model functions, and HScript commands that operate on Houdini standard volumes. And they also should work with VDB volumes as well. They're pretty interchangeable. There are, and we will be using this, is the volume wrangle. And this is volume-based, but it does work with VDBs. The last note on here is that you cannot currently use VDB primitives in simulations. That sounds like a little bit of a shocker, I'm sure, for most people. Pardon me. So that mention right there kind of threw me for a loop. I was like, wait a minute, I use VDBs all the time for simulations. What's actually happening, being that Houdini native volumes, these standard volumes, have been integrated from day one? What they're doing is behind the scenes is your VDB is basically getting converted to Houdini standard volumes to do the simulation. And then it'll, depending on the node or the simulation that you're using, be it DOPS, PyroSolver, or so forth, they will export out as a standard volume or have an option to export out as VDB. So that's one reason why I was pointing out to pay attention to the colors, because you may put one in and you'll get a different one out. So it's just something to be aware of, and just pay attention as you kind of go through things. So another thing I want to point out, and also kind of show these examples at the same time, when I used on the standard volume, we have the ISO offset. The equivalent of that would be the VDB from polygons. And it's very similar. You have the voxel size, you give it a name. This one has fill interior and a few other things. There's a specific thing about this node that came to light to me more recently, and I say recent as in like the last 2 years or so, as far as how this works mathematically and some of the differences in how you're going to use your volume. And if you mathematically need values a certain way, you want to pay attention to this. So this first example is, and I'll move it so you can see the title here, we're converting a standard volume to VDB. So I'm taking an object merge, and I'm actually pulling in my ISO offset from here. So I'm taking that standard volume, and then I'm piping it into a convert VDB. And silly enough, this defaults to volume, so it should be VDB. So we want to convert it to a VDB. So now we can see we go from green to blue, and that pretty much makes our VDB. So I want you to pay attention to the look of it. We saw how it was clipping, like before the, let me turn that back on, the difference in how that looks in the volume. So let's pay attention to how this is looking now when I switch these to some of the other formats. So we can see the convert standard volume to VDB is very similar, minus the cropping, but it's very similar to the standard volume. If we do the VDB from polygons, we can see it's way more faded, and it also kind of clips in even further, it looks like. Now we get a domain that kind of pops in, especially on the sides. This is part of that VDB optimization as part of that. But the key thing is that VDB from polygons is defaulted and kind of meant for SDFs. And that goes back to that whole, what I was saying, interior, exterior where we have the exterior and interior distance from said surface. This is what that's engineered for. So what's happening is we're saying, well, just give me a fog version of that. So now we're getting voxels that are now faded as far as the numerical value goes. So if I was to use this as a mask, if I was to use this to advect anything, the mathematical value that I have, in this voxel versus, we'll say there's a very faint one there, and this one's like right in the middle. We'll say that this is 2, this one comes down to 1, and this one's like 0.2 for that. Mathematically, if we were to use this version, our values may actually be different. We may, pardon me, we may have the same 2 value in here. This realistically, it's probably a little less, but for the sake of argument here, for comparison, we'll say that that's still 2, but we have a steeper fall off that's happening, across here from voxel to voxel. So this may no longer be 1, this may no longer be 0.2, this could be just 0. And this one could be 0.2 now at this point because of this fall off that we're happening in the values. So when you're trying to decide what format to use here, or method, I should say, not format, the method in creating, you want to pay attention to that because you want to pay attention to what are you intending to use it for. So if you're going to need a certain amount of information, you may want to create it this way versus this way. Another option here is this. This is creating a VDB from scratch using the VDB node here. So what we want to do is the VDB node is a way to activate voxels. So you're basically saying, you're creating this placeholder. You're saying, I want a VDB. I'm going to call it density. I want it to be a fog. I want it to be float and be this size. If I look at this, we have a representation of something here, but we don't have any values. And what we have to do is activate those. So we're creating this placeholder and we say, let's activate this. And this is using a VDB activate. And we want to basically use what's called a reference. And let me open that up. So VDB activate does a lot of things, but to create, we need to reference. And there's the default option of bound group. This is basically point to a SOP of your geometry or a bounding, and it'll take that in. The problem is this will only give you the bound. So you will only get the domain part of it. Sorry, I have my thing going. There we go. So you would only get a box, basically, that would be these bounds right here filled up. You wouldn't get the actual shape of the geometry like you do with the VDB from polygons. So to get the shape, we have to say activate using VDBs. So we have to use a VDB to create a VDB. It's kind of like this whole meta kind of setup. And that's what this second input is right here. So the first one is to VDBs to activate, and the second one is the region to activate. So, and the line on this, or the wire, is very faint. I'll grab it so you can see it. It's going over to this fog density over here. So this is a VDB from polygons. So we're using that to then activate the shape that we're getting over here. So what's happening with that, essentially? We are getting our geometry. We essentially have voxels that are here. They are in existence. They just have really, really low values. Like I was talking, the gradient, that fall off that's happening. And that's because of the algorithm for what this is intended for. And that's why we're getting that. So we're just saying, take the voxels. So, and let me output it. So take the voxels that we have from this output and use that to activate here. And use, in this case, a global value. So we can globally set that value. So we're basically take this shape, the voxels that exist, and over here, set the value for those voxels. So now we get a more uniform volume out of this. Let me turn that back, turn the voxels on. So we get something that's more representative of what the Houdini standard volume is. It's going to be a little more blocky, and that's because of the optimization. We get back to the VDB of, deleting empty voxels versus the active voxels. So we get something that's more representative of that. So I just wanted to really point that out because it is a very kind of not really talked about. I didn't really see many people out there explaining these little nuances like this. So I wanted to make sure to highlight that because depending on how you're using these, at the moment I'm saying volumes. So when you're using these volumes, depending on what your intention is what's going to kind of dictate how you make them. Really briefly, there's a wiki that kind of explains what VDB stands for, which is basically nothing. It's just a name. You can read through all of this right here. It went through a variety of iterations that were just kind of made up names, and there was confusion about pre-existing names and so forth. But don't worry about what it stands for. It really isn't anything. It's just VDB. It's a name. That's the actual name of it. I'm going to grab a drink real quick here. Any questions on the VDB side of this?
I think we're good.
Okay. Hopefully I'm not confusing anybody either. We're getting into a lot of the technicals. I know this is the boring part of of the let's do glorious cloth sims and all of that stuff. But this is very important because to do those sims and control them the way you always want to control them, because these are a lot of the conversations I have with students and just individuals out there of I want to do this specific thing. This is a lot of the caveats that you really need to pay attention to because this is what's actually going to make or break what you're trying to do. And if it does break, this at least tells you how to fix it or at least know where it's at, where it's broken. Okay, so next one is demo 2. We're going to talk about the structure of VDB. So we're going to go behind the curtain as it would be. And I'm going to zoom in briefly here because there's a lot of things that are in here scale-wise. So we can see Flippy in voxel form. So the red voxels that we're seeing here, these are the active voxels. The yellow up here is just my density field. That's just a title. And my cursor is going to go crazy because of all of these extra lines in here. Oh, there we go. This is just explaining that I'm using a density field. It's a scalar field. So this is just a general title is all that is. It's not related to any of the colored lines that you see here. So we have our active voxels, and then we have these blue boxes around everything. These are called leaf nodes. These two are going to be the most common ones that you actively will see for the most part. This, and I'll point this out as well, is not some magical thing I'm like generating. This is an actual node. Actually, I'll just create it. It's called the VDB visualize tree. This node gives you access to that data, and you can display the leaf nodes as wireframe boxes or a couple of other options here, solid boxes. You can turn them off as well. There are internal nodes, which I'm displaying and I'll show in a second. There are active tiles, which I'm not going to show. They're very similar to some of the other ones, so it's kind of less important information in my opinion. But the active voxels, this is the most important one because this is where the actual data is. So you can display those as wireframe boxes or points. In here, they're displayed as points or boxes in the wireframe form, so we can actually see everything stacked on each other. But as I pan around here, we can see that these leaf nodes extend out, but they are kind of truncated. It's kind of like a very low res version of Flippy in some respects, super low res. And what's happening, and I'll go to a side view here of, let's see, the front view by hitting 3. And this will be easier to explain. I'll turn the labels off for a second to eliminate a little confusion. And what we have is this is an active voxel in our geometry build. This is an active voxel. This is an active voxel, and so forth. What's happening is VDB splits things into quadrants. There is this basically, it splits it literally into a quad. So on all axes, it's just split in half essentially. And to optimize, and this is what makes it super efficient, is if I have a voxel in existence here that's activated, is it within this leaf right here? Actually, I'll undo that now, change colors just so it's easier to see here. So this quadrant here, is that voxel in this quadrant here, or so on. So what it does is basically, I have a voxel that's in existence in this quadrant. I need a leaf node here. So it creates one. It's mostly empty for the most part because there's a single voxel in it, but that is needed to basically house that voxel. We have ones on here that are probably better used, that are more full. There's less empty spots in there, but that has a leaf node for it. Same over here. This one only has 4 voxels, and this one only has 2. So this is how VDB stays super efficient. It's like, I don't need information out here, so I'm not going to build it. So I'm only going to use these leaves right here and create these voxels right here. Within that structure, there's the internal node. So there's a larger quadrant that's built, and I'll turn that on and go to perspective because the text shows up better. So there's an internal node quadrant set up like so. And you can see that all of them except for one on the corner here is needed in that case. And that's based off of the leaf nodes. If I don't have a leaf over there, I don't need these quadrants. And then there's another level, which is kind of like the master level of internal nodes. Same exact thing. So there's a master quadrant over there that's not needed. So this is a massive hierarchy that's happening behind the scenes without you having to think about it. And this is what's making VDB super, super optimized. And if I zoom it in just enough here, I'll do a VDB slice here, and I'm just going to hack away so we just get like a section of this. And you can see as soon as I did that, we don't need all of the other leaves. We don't need the other internal nodes. We immediately only get what we need. And if I was to move that slice through, you can see how this updates accordingly. As it needs a leaf, it creates a leaf. As it needs an internal node, it'll create that, and so forth. So this is how VDB stays super optimized. This, however, is also exactly what causes our issue with popping for velocity fields. As the velocity gets activated, you'll see a leaf node pop on. That gets activated. That's what's causing the glitching and everything. I'm going to show some examples of how to deal with that in another section here. But this is what's happening with the VDB structure overall. I just have a couple examples here. This is basically a velocity field version versus a scalar field. So what you're seeing color-wise here, the red are still active voxels. The white technically are as well. The difference being is I want to say it's the white has negative values in it. So either X, Y, and or Z has a negative value in there somewhere. So I'm just doing that to represent the shift in that. And I can flip this over to show the arrows. These are the vectors for those voxels, which is just a generic noise that if I scale it up, we can see how that shifts to negative, positive, and gets more frequent and less frequent, so forth. And then this is just showing the actual voxels location in there. So that, I believe, covers that. The link up here is going to the OpenVDB docs. If you want to actually deep dive, and if I go to here, that's what this link does. This is the actual source. This is the home for OpenVDB. So if you are like into C++ and programming and you want to like really, really understand OpenVDB, this is where it's at. This is all of the data. You can go here, check out all of how to build any of that stuff. It's well over my head. This is about as far as I get with the technical understanding of it. Once we get into the coding of it, I'm lost with C++.
We do have a question, David.
Sure. Yes.
It's related to the previous section. James is asking about when do you decide to use a native Houdini volume versus a VDB volume? You're showing these options, but how do you make those decisions of like, are you going to use one over the other? And do you still use ISO offset and like VDB activate versus, convert VDB, for example?
Versus
Yeah.
converting versus
Like when would you
like
use
those
one
three
over
options.
the other in
It
circumstances?
it primarily, so for me personally, this is legitimately the first time I've used ISO offset since version 13. I don't use that. I pretty much stick with VDB for the most part and the other like volume nodes, but I don't create fog volumes with the ISO offset anymore personally. I couldn't say specifically if there would be a benefit outside of, say, memory requirements or compatibility. So I haven't encountered anything specifically offhand, but again, I'm sure there's an edge case out there somewhere. I pretty much stick with the VDB ones because it's just, I find it more efficient overall. And since Houdini automatically does the conversion for me for the simulations, like that note about saying the VDB primitives aren't used in simulations, that you
Yeah.
can't use them. So I let Houdini do Houdini, like let it take care of as much of it as possible. As far as choosing between the three, it kind of varies, more specifically probably related to what I was just explaining about the mathematical reason. I would say that's probably the heaviest uh, choice to make, is whether or not I need mathematically something with a fall off or something that's more one-to-one to my volume, with a global value across the board. If you need something that's, exact, like this is all one values, every voxel in here that is active is one, whereas this one is going to be one, and then there's like 0.5 down to zero. So there's a gradient happening there. I would say that's the biggest determining factor personally. Other users may have other reasonings for that. Beyond that, I haven't seen too much of a difference when it comes to like overhead offhand. I haven't encountered anything that just blatantly says, "Oh yeah, this is way faster than this." But
Right.
I'm sure if you did the what's it, the performance monitor,
Right.
it would tell you differently.
Great. Yeah. I think James is also wondering about, do people still use ISO offset or like legacy? I think it is legacy. I think
It
that once
probably is
VDB
legacy.
came out, everyone kind of switched to
Yeah,
VDB.
it's the optimized holy grail. Everybody's using it. It provided easier options for like modeling and so forth and all of that, just because it was more efficient and optimized. And I think everybody just kind of latched onto it. So yeah, the ISO offset kind of fell into the background and mostly is legacy. There's a lot of old users that
Yeah.
have older versions of their project files that just need that, or just more familiar with doing it that method.
Okay. Great. Thank you. And thank you, James.
Yeah. Any other questions?
Yes. Is there a way to visualize volume or VDB scalar values on the viewport?
So I have a setup for my presentation that you could probably adapt for yourself. There's no native way that I know of other than using a slice. So if you did the was it VDB or volume slice is what it's called, and forgive me, I'm
Isn't
gonna.
there also a volume visualization node
Well, there is a
inside?
volume visualizer as
Yeah.
well. I think, yeah, which gives you some options. But as far as the numbers, like say the voxel values, I think this will only give you like a color representation. So you can, show the emission, show the smoke and so forth. I don't think this gives you the numerical value specifically. I could be wrong. But like say in this case, if I had this VDB, I'll go here, look at the slice. So we get the slice, which is also colors. So you have mesh, a volume version, or points, any of the above. But if you go to your geometry spreadsheet, this outputs it, and you can give it a name. So say my vowels, just so it's readable here. Oops, move that out of the way. And we'll see that my vowel shows up. This will be per point. In theory, each point is each voxel. So if I did that, within that slice. So that's what you're looking at right there. And then that would be your value. That would be probably the easiest that I know of to get the actual literal value in a visual form.
Awesome, great. And you
Right.
can always go into D for display and change your visualizer to numeric if you wanted to as well.
Yes.
Cool. Thank you so much.
Excuse me. So we talked about that one. The last part of this section, and I'm already looking at my clock. We're at an hour 15. I am definitely going over today. So we will take a break at a certain point because I know we'll need it. And I may actually carry over some of the information. We may take this section possibly into the next session, which is okay. Because there is a lot of information. I tend to go overboard when I pack these things. So VDB structure we did, SDF. So let me close this up. So SDF. First off, I want to highly recommend, let me pull up, where am I? Oh Lord, too many windows. Here we go. Right here. Peter Claes, the OG Houdini guru. He's done so much stuff, but he has this incredible SDF series. I definitely recommend checking it out. Sorry, as I take a drink there. He goes deep diving into this, and I think it's it's 3 parts. I would definitely check that out in your free time if you want to like really understand SDFs beyond what I'm going to explain, because what I'm explaining is pretty much the extent of how we're going to be using it, which is essentially hopefully this cough will go away. It's really getting in the way. So with an SDF, we see a voxel representation, and it looks very different. It's not fog, like what we were seeing with these earlier ones, like so. I scaled this one up larger because it was easier to kind of illustrate what I'm going to be showing here in a second. So we get this crazy kind of blocky looking thing. If I was to like zoom into it, we can see inside of it. So it's hollow. There are options to not make it hollow. Essentially, you can fill the interior, but I'm going to go to a slice version of this. So I'm going to hit SDF slice on this particular thing here. And this is a whole rig. I'm not going to show all of this, but you can definitely dig into that if you want to just see how I built the presentation. Same goes with all of these. But this was less important. It's more about this explanation than it is the actual build that's happening in here, because it is kind of like hacked together in some of the aspects for slicing everything. So we're doing a clip and all of that. We will talk about VDB clip when we get into masking and stuff. So don't worry, I'm not completely ignoring it. I will go over it. So what we're going to see in here, and I'll go to 4 for this side view. I'll hit 4 again so he's facing the other way. And hopefully you can see these. There's red points and there's green points that are in here. I'll even, well, it doesn't get bigger if I zoom it in. If I hit D and go to geometry and points, there we go. I'll do it like that. And we'll make it 10. Hopefully that should be nice and visible. So what we're seeing here is we've taken a slice of flipping along the z-axis essentially. So we're looking at the x-axis, looking along the x, but we sliced it along z essentially. So that curve, the white line that you're seeing around there, that is the surface of flipping. So that is the representation of that surface. And I'll move this over to here to kind of get some more of the details of it. We can fill the interior, and we'll see that we now have points going all the way through the interior of flipping. So what SDF is doing, like I said, is representing the surface. So there's a series of voxels around the exterior and the interior of that to represent the surface. The distance, and let's do the voxels. So this is the voxel representation. These are where the voxels are roughly. My points are truncated. A lot of the glitches that you'll see, like this empty voxel and possibly a stray arrow, is more having to do with how I built the presentation than it is the actual SDF itself. So keep that in mind. This is just a byproduct of how I built it. But what these usually default to, you'll see exterior and interior. And I'm just going to pull up the actual node just so you have context here too. VDB from polygons. So it defaults to surface. So that's giving you the SDF. So that is literally this version right here. And you have exterior and interior. So you have these, what they call band voxels. So there's a band of these voxels going around it. And you can increase those and decrease those, essentially. You can't go below 1, obviously. If there's no representation, then they can't represent the surface. So you can expand that out. And this comes in handy for a number of cases. And I'm going to say specifically when you're doing flip simulations and colliding. If you have a collider that's SDF, currently there's, I want to call it a bug. I don't know if that's a known thing or not. But before, earlier, when we were looking at our domain, and that domain went right up to the voxel, change my color and go to this. So right here, that intersection point of the voxel hitting the edge of our domain. When that happens for the flip colliders, for some reason, it seems to want to ignore the collider. And you need to basically just bump this out to like 10. For some reason, once you do that, the buffer, I guess, of this now makes it so the collider is recognized. It's a weird glitch. I want to file that as a bug. I'm not sure if it actually is a bug, but doing this usually tends to fix it by expanding that out. But I just want to illustrate how this functions. You know, we're filling interior and exterior. And what that gives us is this gradient, essentially. If I flip it over to fill interior, actually, sorry, I have to expand this up. There we go. Look at the gradient. So we can see, I'll turn the voxels off for a second because it does get a little confusing there. So this is the gradient that is happening. Basically, our distance from our surface. So surface here is a value of 0. Then it propagates out in a positive fashion. We'll say this is 0.6, and this is 1.3. Going inside, we have negative 0.2. Whoa, that tripped out. There we go. And we'll say this is negative 1 in this case. So these values will get lower or higher and higher, but in negative, till it hits a kind of central zone of sorts. That's kind of equidistance, you know, from this surface and this surface for the most part. So it does kind of hit a center kind of gradient dividing section. And this will actually travel throughout the whole thing. So if you thought of a almost like kineffects, if there was a skeleton inside of Flippy, it would kind of be roughly almost like this, you know, where these merge, these values merge to a center point where it can't go any further. Pardon me. Let me get a drink here. My voice is acting up. Okay. So like I said, this is 0, and then it propagates out positive and propagates in negative. So that is the representation. When you say fill interior, you get all of the values going to that center line, basically. When you don't fill interior, you're basically limited to that voxel band itself. So you only get, you know, 3 voxels in or 2 voxels, whatever value you ended up choosing for your overall setup in that. So if I took that up down to 1, I would only get 1 voxel in and 1 voxel out value-wise. So that is the primary functionality of SDF in this case. And when you do colliders in simulation, that's exactly what you're looking for, is that surface, you know, because you want it to collide with the surface of your geometry. Sometimes when you use the geometry itself as a collider, there's basically under the hood functionality that's kind of mimicking that kind of process for the most part, where it's getting converted at some point. But when you create your own SDF, that's exactly what's happening with that. So that's the important functionality part of it that we'll kind of discuss. And like I said, to fully deep dive that, like really bad, or not bad, but very deeply with Peter Clay's, check out that series on that. So any questions on the SDF section of this?
Any questions, anyone? That was really cool, David.
Cool. How's everybody feeling so far? We're at 1 hour and 24, it looks like. If anybody's feeling like they need a quick break or
Do you
anything.
need a quick break? Because you might need to
I
get
mean,
more tea or
I've got water. I literally have a huge cup of tea here, and I have a backup water as well. So I just have to be a little more frequent in drinking it.
I think we're good. I mean, I think
Yeah, no,
any-
I'm good to go if you guys
yeah,
are.
yeah,
Okay,
I think we're good.
cool. All right, let's hop on over. That was just the first section. So sorry about that. It's a lot of information. Once I get started, I start finding things and I start adding things. That's just how I am. And I don't want to
All
miss it.
good. Don't worry.
You can't say you are not informed when you take my classes. Let's put it that way. So next section, field creation and subtleties. So this, I'm gonna go to my side view here, which is, or the front view, I should say. I hit H. And again, there's a bunch of presentation stuff that's all happening in these closed up network boxes. What you want to focus on are the yellow across here. And I'm going to have, these are all vector based and these are all scalar based examples. And this is where we're going to show a little more specific of what those voxels are doing and happening, and also how to build the different formats. I showed the 3. These are a couple other variants as well. So let me grab my controller, unpin and pin that. And let's also run our fix font nodes just to make sure that is working. So if I change these, or actually more importantly, let's do this. I should see, there we go, my titles are changing. Good. Awesome. All right, so what are we looking at here? This crazy monstrosity. So we have just the general title up top. We're dealing with a VDB scalar field. And this basically is just kind of dictating the method in which we're creating said field. So we're using the VDB activate in a domain fashion, and we will look at the actual nodes. So we do have them right here. And it's just gonna, I'll explain all of that. So this first section over here is going to be the actual fog view of the field. And I will note, we are now moving over to the field terminology. I'm going to do my best to hopefully not forget. And we're going to be referring to this as a field because that is what it is called when you're in simulation, with Pyro simulations, especially when you're dealing with fields. That's the terminology that's being used. So technically in the geometry level, you're dealing with volumes, but I'm still going to use the field terminology because that's the intention for a lot of these things that we're building. These velocity fields are being built either, in SOPs or within the sim itself. So that's why we're going to just kind of stick with that terminology and hopefully not forget on my part. The second here, this is the voxel tree. Let me take the voxels up a little bit. It's partially more visible. Let me take my point down. That's what's mostly doing it. Take that down to 5. Okay, come on. So we can see our points. So try to find a midline. We'll say 4 in there. Okay, perfect. So these are the representations of the voxels, but I'm just doing it as points instead of boxes. Over here is going to be the volume trails. So this is a visualizer when you're looking at the trailing of the values of your voxels. Now, in the context of scalar fields, we don't technically have any direction happening. We have a single float value, a scalar value. So in the context of scalar fields, we're going to turn that off. We're going to say that does not apply. We're going to use that for the velocity field. So when we get over the vectors. And this last one is the VDB slice. Basically, it's our voxels again, but I came up with this fancy little slice deal here so we can look at the sections of that slice and look at the actual front to back. If I turn this back to perspective really quickly, this other controller right here is actually slicing front to back within that actual field. I'm just going to leave it at the center, but I just wanted to point out that you have that option if you want to play around with it. And let's see here. I'm looking at my slice value. I'll just keep it at the bottom for the moment. So what I'm building in this particular case, this very first setup, is we're dealing with a VDB activate. So we're using the VDB node. And I should point out too that we're using VDB for all of this. So I'm not doing Houdini standard volumes because we're going to stick with VDB for that efficiency aspect. So this is the VDB node. Again, shouldn't have to show this every time, but I'll just show it briefly again. Actually, I'm typing. I shouldn't type. There we go. So VDB is going to be this node here, and we're going to be grabbing various nodes from this collection. So VDB, we are setting it to density, and we're giving it a voxel size value. I will turn this back to my default of 0.1. And that is pretty much all that's needed on that. So we create that placeholder. We say we are creating this actual input VDB to activate. We're not going to activate a region in this particular case. We're just going to take it as is and say, give me a 5 by 5 by 5 region and make that value 1. So all of those voxels are 1. Visually, you may see a slight gradient there, and that's just because of how the OpenGL visualizes. If you turn off the lighting, you may get a different look to that, but that's the reasoning for that. So as far as the voxels, let's take a look at the values. If I click this little box here saying show values, keep in mind, this is very heavy. This is not super efficient, the way this shows this, especially on the vector. So be mindful of that when you try to scrub around with these values showing. But we can see the value of every voxel, and we can even show a representation of those voxels right there. So these are all 1.0, and that's should be right because that's what we set. We set this to a value of 1 across the board. We can switch this, kind of full screen that again, to the next output, which is using VDB activate to do a shape. So same concept. And this is similar to what I was showing earlier. So it's VDB density, set that voxel resolution, and then we're activating with the VDB activate. We're going to do a value of 1. So all of the voxels that we activate are going to be 1. We're going to use that reference. Open that up so you can see it. So the reference tab, and we're going to activate using VDBs. And that VDB we're going to use is a fog VDB from polygons. The voxel size is linked, so we have the same resolution. You do want to make sure that those match across the board. Otherwise, you get some weirdness that happens. So a value of 1 using the voxels that are created and activated within that zone. Now, I did not fill the interior, so we do technically have that band around there. And we can see that based on the values that are happening in here. I'll zoom that in a little bit more. We can see the interior is all like 1 values, 0.5 for a few fringe voxels that just don't quite meet the requirements of in or out. So we get a few that we can see represented there. And then 0 for the ones that are outside of it. And to show another variant, is going to be VDB from polygons with the bands. I'll select this one. So VDB by itself with the band. So we are taking the VDB from polygon directly now. So versus the previous, whoops, wrong one. Come on, go back. There we go. So versus this one where we're activating a known global value versus taking the VDB from polygon directly, piping that in. We're just taking it directly, so we get this right here. So we can see that kind of gradient. There's that in the middle just because of the pig's nose. If I move that slice further back, you can see that his ears are in there and the rest of his face is in there as well. So I'll go back to the numerical values, and we can see here now the gradient happening across there. And I'll even scoot this up just a little bit to try to get some of the other voxels. So we can see the value of 1 for that interior, and we can see that gradient of how it tapers off into basically 0 for outside of here. And another variant for creating this is with the fill interior. So we can see the variance of how that affects the values in there. So we can see how that shifted, not only just color-wise, but the value-wise across there. So now that it fills the interior, it'll actually taper those values all the way in. So we're seeing a lot more of a gradient aspect there. I'll even scoot this up a little further towards the center section to kind of see that. So we can see kind of like that central section of the pig right there, and how that tapers off eventually to the 0 across there. One thing I'll note is if you do change the voxel scale on this, I'm keeping mine at 0.1, but I have the option there. If you change that, the vertical count changes, and there's no way for me to dial that in specifically in the UI. So my max value of 38 in here works for this value, but if you go to higher values, it may break this down here. Just be aware of that if you're playing around with it. So that's a known limitation of this particular setup.
David, could you explain bands?
Yes. Bands being the voxel bands that we were talking about with the SDF.
Mm-hmm.
So that representation of the surface. So if this was the profile of, say, Flippy, with his mouth or whatever, and the surface itself is 0, and the band is those voxels that step out from that. So and it actually would be easier just to show. Let me hop back into that and just go to the SDF example right here. H1, yeah, and turn on the slice. So the bands being the voxels that we are seeing. I'll take this down to 2 so it's a little easier to read. These voxels. So the slice of the surface is that line, and then the bands are basically the interior band are these red voxels, and the exterior band is the green voxels. So those are the representation for the surface. That's how it calculates the surface of an SDF. So that's what that's referencing. So when we get into this display right here, there we go.
In regards to a scalar volume, though, it's
in the scalar, it's still the same. It's representing still that boundary that's happening right there. You can see how the value kind of separates. It's still doing the same thing, but being that it a scalar field in this case, it does propagate to the center. But when you do the fill interior, it does like another operation on top of it that properly fills the interior. Is really bizarre because it's not technically empty on the interior for a scalar field with the VDB from Polygon specifically.
So if you don't fill the interior, you get a gradient. If you fill the interior, it kind of fills it with a 1 value for density.
With a correct gradient, I think would be the way to describe it.
Okay.
So there's a gradient and then another gradient, if that makes any sense.
Thank you. Yeah.
So that's essentially what's happening with that. So yeah, that's what the term bands is talking about, that interior and exterior surrounding difference of the surface. The other output that I was pulling up, so we did this one, which was VDB filled, and then this last one here, excuse me, is taking our geometry surface directly. So I have the source geometry, it's just the pig head is all it is. and I'm scattering points on it. And I'll full screen that. So I'm just scattering 10,000 points on the surface of that geometry. I'm then taking an attribute adjust float and converting that, basically saying, let's create a density attribute, give it a value of 1, set initial. We're not going to, I think it defaults to add or one of the other ones. Since there's no incoming attribute for density, we can't add to it. So we want to set the initial, and that gives us a density attribute. And then we're just going to use the volume rasterized attributes to convert that into an actual field. And that's what we're getting over here. So this gives us something similar to how the SDF works, only in the respects that it's near the surface. There is no distance fall off math that we're incorporating into it specifically. We're not saying, make the surface 0 and any point beyond that a different value, because all of these points are sitting on the surface. Actually, if I make that active and I'll template the pig, we can see that those are all pretty much just sitting on the surface itself, along that actual edge there. So they're not inside, they're not outside, basically. But what we're basically trying to do is just create a field from all of that to get this representation of the surface as an alternative method of creating a field based off of a geometry shape. So we're just scattering points, giving it an attribute, and then converting that with the volume rasterized attributes, which is a pretty common workflow using this, taking an attribute and converting it to create a source. And you could inject noise into this. Instead of a constant, you could use a noise or a random, and this could be a pyro source of sorts that comes off of the surface itself and not the entire object, since it's not filled. So let me go to 3 at H. So the representation of that right here, we can see the values on this, that we have 0. I'll scoot it up just a little bit more. 0 on the interior for its values, because that's all empty. And we have 0 on the exterior, because that's all empty. But we do have somewhat of a gradient. And why is that? That is basically because our points are getting rasterized. When they get rasterized, they're getting rasterized to a voxel size. Well, that size in relationship to my geometry size may be bigger, or it could be, equally matched. So if I had a larger voxel size, I'm encompassing a larger area. Therefore, the values are going to kind of like taper a little bit. It's not an immediate sharp fall off with where the voxels are at. So that's why we're getting not a solid, say, value of 1 across the board. We're getting a taper of this gradient going in and out as well. So I just wanted to illustrate that visual. So those are a variety of ways to build a scalar field, and just some of the subtleties of differences within those different methods as far as having values inside, outside, on the surface, or gradient along the line. So any question on this one before I hop over to the vector version?
I think everyone's good.
Awesome. So let's hop on over to here. And I'll take this back just because these are heavy. And let's go to this one. And we do have the velocity field, so we will keep the volume trails up for this one. Same exact layout. So we have the fog, we have the voxel tree over here. That same note about the white versus red, those are negative. They contain negative values on one or all of the components, X, Y, or Z. The volume trails, which if I go to perspective, makes a little more sense. We can see the curving of that. It's basically a noise field that's happening in there. So we can see the direction of everything and how it's working. And then the slice that's happening over here. Same front to back slice, so you can slice through that. The only other difference is that I'm not visualizing it in color. And that's because since it's velocity, it's a vector, it can go negative. And I can't represent negative colors in color because it just, once it's black, it's black. So I just converted this based on a loose algorithm of just taking the length of the color and the absolute value of it. Don't worry about the mathematics of that. It's just so I could visualize this in a easier way so it wasn't disappearing and not functioning in a visual form. But that's the equation I used basically for the velocity values that I extracted to get this color scheme. So the first example is, again, going with the VDB setup, and it's going to use the exact same nodes. So we're doing VDB and VDB activate. The only difference is that we're obviously changing our name. This is a vel field, and this is a data type, which it should say data, but it's the type of vector. We're not doing a float anymore. We're doing a vector. There are other options in here. H20, I should point out, is starting the path to adding new types, data types for volumes. So you want to kind of start paying attention to these. It used to be just two, vector and float, but now we're like getting into some new ones. So we're going to have matrices and quaternions, and I forget a number of other values that possibly we'll have access to in the coming years or months, depending on how they add those. And they show a lot of that in the VEX code that we'll show later as well. The vector type on this is basically a displacement velocity acceleration. So the reasoning for this, so you have position, basically velocity, unit normal, gradients, color, if it's a tuple. This plays a huge part. If I middle click on this and you see the vector 3, we get back into these formats. When you are exporting, and this is like a massive issue a lot of people have, exporting attributes, exporting volumes, anything that they're exporting, the data type makes a huge difference when it's going to another DCC. Vector 3 might be readable, whereas 3 float, which is a possibility for a vector, is not readable by that. So the representation in Houdini may be 3 individual floats to make a vector, but for the exterior apps, they're actually looking for an actual vector type. So that's where this all comes in. So you want to pay attention. Like if you're dealing with a color, make sure you set that type to color. If you're doing displacement or acceleration velocity, make sure you set it to that. This option exists when you manually set this up. When you do VDB from polygons, you don't get that option. You get what it gives you. Float for the fog volume, and I believe SDF is float as well. Probably break some stuff here. Yeah, just straight float values for that as well. To get to those data types, you got to pay attention to that, and that's one of the key reasons why I'm showing the 2 node setup where you're building stuff from scratch. You have access to a lot of information that is really important in some scenarios. So you want to pay attention to that. So we take our VDB, reserve those voxels, we activate those voxels, give it a base value. And in this particular scenario, I'm just adding a noise using a volume VOP. So we're going from VDB nodes to Houdini standard volume nodes. But this is where that interplay works. So we can actually use these volume nodes on VDBs. Inside here, it's just a really basic thing. I'm just adding curl noise to basically eat away at this field to create the swirling that we have going here. So I'm just taking the position going into a curl noise. That's coming out to multiply against my activated volume field, excuse me. So the activated field that we get here is basically a solid block because that's all we activated. It's a value of 1 for that sizing because we're not doing a shape. So once we come into here, I'm saying, give me that input, which is input 1, and using a volume sample node. Bring that up. So you're going to see in VOPs, you'll see volume sample and volume sample vector. If you're doing velocity, if the input is a velocity, you can use the vector. If it's a scalar, you use volume sample. So you'll see the volume sample V for vector is what we want right here. So we want the input of the first input here. You just connect that straight across, and that is just referencing that first input on this node. And you can also alternatively change it right here, say first, second, third, fourth, whatever. And then we need the sample position. So what we're saying is sample the current incoming position, which means our block that we're using, we're sampling that position to then multiply the curl noise against. So if I should actually reverse this because the curl noise is underneath for the multiplication. So we're reading the volume or the field and then multiplying that against it and then outputting that out using bind export, which is going to give us the export for that, and make sure we call it vel to match our incoming field. And that gets us this nice little noise field, really basic standard stuff that we also showed in the first class in that regard. So let's bring these back. So that is one method in creating a field, a velocity field. We're going to switch it over to the next one, kind of reiterate a little bit here. So we're doing the VDB, again, activate using VDBs. And this is how we get the shape. So again, remember that importance of being able to set that vector type is because of this VDB. So we're using this method and then using VDB from polygons to get our shape and then activating that on that second input. We're using the exact same noise in this regard right here. So we end up with, I'll show the values on this. This one definitely takes a little bit longer to show because we're talking about 3 values now per voxel across the board. There it goes. So we can see what those values are. So X, Y, and Z, it's top to bottom is how I stacked them for all of those. So we can see that, and then the representation of the voxels that they're associated with. Do not try to scroll this with the numbers showing. It will totally churn for a bit, but I can show another section here. Hopefully you do not hear that leaf blower in the background. It sounds like they're doing some cleaning.
We cannot hear it.
Excellent. This microphone's doing wonders. All right. So we can see the difference values on that new section right there and how they kind of dip down and raise up. And the noise on this, so we can see the curling of the trails of what we're getting for that velocity field. Turn that off. I'll take that back down. So this is, and let me make sure I'm on my output, and there we go, fixed nodes. My information wasn't updating, so make sure I fix those nodes. So the output was activate domain via VDB from polygons. This next one, let's hop over to here, is using the rasterized attributes. So we're using, in this particular case, a points from volume. This gives us an actual representation of the interior. It just fills our shape with points. You can put this in geometry, you can put this on a volume, either or. This tends, when you have it with a volume as a source, it will be 1 point per voxel. The general point separation is basically equivalent to the voxel size in that regard. You can change the point configuration to tetrahedral just to kind of give it a staggered look. It's not grid. In this scenario, if you're dealing with volumes and fields, I would keep with the grid setup just to make sure everything lines up. So I'm taking that points from volume, same point separation, putting that into an adjust attribute, adjust vector, setting it to vel. And same thing, we're going to set initial. In this case, I use the noise for that. So instead of doing the VOP noise, I'm doing this through an attribute adjust vector. Make sure it's 0 centered. If you want negative and positive, it defaults to positive. And then put this to 2 and an element size of 2 for this, just to kind of push things around. I don't have this animated here at all. This is all static. And then a volume rasterize attributes. So we're mixing volume-based stuff here for this method, keeping VDB across the other setups. But we are getting a VDB output for this. So the volume rasterize gives us that. So this is one of those confusing moments because this was not a VDB node, yet it is outputting a VDB. So this is where they've kind of tried to merge and blend in how they somewhat unified the standard volume with the open VDB volume. For the last reference here is using a long surface, same concept, scattering on that surface, doing the vel, in this case, zero centered and noise, literally the exact same setup. We're just using the scattering method. So we now have values that are going to be along only the voxel area. So it's zero inside, zero outside, and just along that surface. As soon as that pops up, there we go. So those will be right across there. For the most part, they'll be somewhat unified until you get closer to the edge because they do taper off just a little bit here and there. So we get zero in and out on that. And that is the end of that section. Any questions on that? It's very similar to the scalar one. I just wanted to show the variations of those differences in there.
I think we are good.
We're good. We are coming up, I'm noticing, on 155, the 2-hour mark. That's really heavy there. There we go. I do have 2 more sections. Doing those will definitely, I'm willing to basically move this over into the next session. For this, I kind of overpacked, it seems, because the field masking, we have a couple of builds here that also has a couple of individual things. So I could probably get through this in a timely manner. I don't want to hold everybody up way too long. This is showing a few other things to basically help you troubleshoot and understand some of the unknown areas of these fields. But I should be able to get through this one, I would say, within the maybe 30 to 45 minutes roughly. And we can take a break before we start this if you like.
I think keep going.
Keep going?
Yeah. If
Just
you have 2 more
power through it.
sections. Yeah. Unless someone needs a break, unless you need a break.
I'm actually good. So it's up to everybody else. I know we talk about 2 hours and I just don't want to like bludgeon everybody to death.
No, it's fine. I think let's get through this section. We'll take the temperature again.
Okay. We will go through them. So in here, let's select that, make sure I get my controller. Let's make sure we fix our nodes. And I'll zoom that in. Actually, I'll turn this to perspective by hitting 1. And let's see. Okay, should be good. If I flip this, that should change. Good. Awesome. So field masking. And let me bring my notes up here just to make sure I'm touching on the right stuff here. So this is just going to be a simple scalar setup. And this is to kind of accentuate optimization, essentially. We're getting back to efficiency and optimization, hidden things that you may or may not be aware of with the VDB fields. We activate voxels like we did before, to create such things here. So I have the exact same setup, doing a VDB here to create density, activating it with a value of 1, VDB from polygons to create the shape. Same standard thing. I'm doing this for the face. I'm doing this for a pig head, which is hard to see because it's inside. So there's the geometry of the head and the pig sits right inside the head, like so. And I want to use this to illustrate a little weird, not really weird, it's just a not so obvious issue. So methods for masking. I'm just simply doing add, subtract, and multiply. So we're going to do add, subtract, and you'll see a difference there, and multiply, you see a bigger difference, obviously, just to illustrate these kind of issues. Nothing really to talk about here for the build of that. It's just clean up and centering the object. So we don't really need to go over that, which is good. These are the primary ones, and we've kind of talked about that already. So we don't really have to dig deep into the activate and the VDB from polygons. I'm pretty sure I've made the point on that. In the volume VOP here, this is where I'm doing the addition, subtraction, and multiplication. All I'm doing is taking the position of the input. So the input in this case is our face. This is going to be the A density, and the pig will be our B density. So that'll be the second input in this particular case. So we have the initial face coming in. The read, we're doing volume sample in this case. This is a scalar, so we're not doing the volume sample vector. So it's just the volume sample there. Coming from the second input, this is getting our pig. And I'm just piping that in as a multiplier. So these are all just multiply, subtract, and add, essentially. And I'm saying take our density and piping that into the add. And then I'm saying take the pig and add it to it. Doing the same thing, saying take the pig, subtract it from it, and multiply it. I'm feeding it. This is just for my presentation. I'm doing it in a switch so I could toggle easily between them. There's a parameter for that, but you could easily just take the output and put it into the density directly because it's just going to output the result of each of those. I'm just doing this for convenience so I can toggle through them without diving in here. The rest of this, you don't need any of that information. You can check that out on your own if you're looking for tech stuff. The VDB tree in here, I'm just going to point out this node because we're going to talk about the hidden little thing here. So I'm going to show the slice of this because it's easier to illustrate and see what's happening. We can also see the addition happening. Each of the fields, the face is a value of 1 across the board. The pig is 1. 1 plus 1 equals 2, which is why we see this one a lot easier than we see the face. Nothing exists outside the face, so we have 0 out here as far as voxels go. If I look at the voxel tree, we see the leaf nodes, we see those active voxels. We expect the face to have our voxels because that's what we activated. I'm going to go to the next method where we subtract. So now we've subtracted this. We've punched a hole in the middle of this. Now let's look at the tree. We have the exact same thing. So if I go back to the add, they look identical. Well, why is that? Well, let's take a look now at multiply before I explain it. If I visualize the voxel tree on that, we have the exact same thing. We basically have activated voxels. We said reserve these voxels, this space, this area, these leaf nodes, and we're going to put information in there. So we did that. Now, as a post operation in this volume VOP, we're saying, oh, let's subtract this. Let's cut a hole in this, kind of like a Boolean of sorts. Let's multiply it and do this. But we're not saying, hey, let's update our voxel grid and let's get rid of the information we don't need. So what do we have to do? We have to deactivate those voxels. Basically, any voxels that are 0 or within a certain threshold. And if I go back over to the subtract, we can see that there's now a hole punched through there. We physically do not have voxels occupying that space. We do not have memory. We do not have storage that is occupying this information now. And that all boils down to, again, the VDB activate. It's very counterintuitive. Like I said earlier, it does a lot of different things. We used reference before to create those, to activate those voxels. Well, the tab next to it is deactivate. So now we can deactivate those voxels. We can do it based on a tolerance and start like hacking into values and so forth. And that's basically what that does. It'll erode into voxels based off of mostly the gradient. So you can just kind of play around with the tolerance on that. But this is a very key thing that nobody really talks about. And I have not seen this shown anywhere as far as like, if you're dealing with volumes and fields and building stuff, sources, you want to pay attention to this, definitely. So that is pretty straightforward. I assume there's no questions on that. We're just basically optimizing the field in a way that we can just pull that all out. But I'll ask anyway. Any questions on that? Sorry, I'm
I
getting a
think
drink too.
we're good.
Cool.
Oh, we have a question.
Yep. Yeah, go for it. You can go ahead and unmute and ask the question if you like, or type it, whichever's easier.
Explain more about the volume sample function.
The volume sample function in the regards of VOPs is this. I will be specifically talking about the VEX one in a very separate section. So we will get into details on that if you're referring to the VEX version. But as far as the VOP version goes, let's go volume sample. I think I have the, scalar. So here's the scalar version. This is the vector version. Basically, you need an input. File name is what they're referring to, and that's going to be up here. This is basically similar to the first, second, third, fourth inputs, which would be those nodules that you have up top. So 0, 1, 2, and 3, but they're also referred to as first input, second, third, and fourth input. So that's where we access information. So we would connect that up in this regard, assuming, I'll put it on 3 here. We assume we have a velocity because this is a scalar, so I don't want to confuse you here. This is a vector coming in. So we get that. We're saying which primitive number. So one thing to note, don't do that. Don't put an expression in there. There we go. If I come back up, when I middle click this and we see this name, there's the, most times you're going to have density, velocity, temperature, like you'll have a series of fields. They stack and they are numerically numbered similar to this zero-based array. So the top name is going to be 0. The next field is 1, then 2, then 3, then 4. So what this is asking for is basically the primitive number. So is it the first, second, third, and so forth? I don't like that. I like switching this over to name, and we get verbatim. I want my vel field, or I want my density field. So this is when you're troubleshooting down the line, this is very important. This helps you way more than 0, 1, or 2. So I always like to change it over to name, primitive name for that reason. So in this case, I would say vel. And then sample position is basically you're trying to tell the system where you want to sample within this grid. If I turn the tree on, it makes a little more sense because we have the voxels. Actually, I got to do my output. There we go. And I'll go to a side view so I can just zoom it in. So what we're saying in there, it's saying, where should we sample? It's like, well, I want to sample here. If I had, in this case, a curve coming through here, and I'll just make a different color. I have a point on the curve, so forth. So I'm saying, give me voxel values on the positions of this curve. These are 2 separate objects. I have, a curve node here, and I have a field here, and I want to find voxel values from this based on the points of the other object. So that's what's happening. You're saying, take this position and sample it. Whatever voxel is in this position, give me its value. So that's exactly what's happening right here. So that sample position, we're just saying, for this scenario, take the current inputs. So for this particular case, clear this out, this field has position values at each voxel. So that's what's reading. Position will actually grab each voxel based on those positions and sample this density. So one of the caveats from that, kind of point that out too, is that because of the order of this, we have the face coming in first as our A and the pig coming in as the B. The B field is basically getting dictated by the A field. Since we're sampling by position here, this position is based off of that first input, which means we can only sample within that range. So if our B field actually extended outwards from here, if it went out here, all of this would be ignored because we're actually sampling within these bounds. So that's just one little caveat to kind of take note of. But that would be sampling for the volume. Hopefully that answers your question. The only difference with the scalar one is that you're dealing with scalar versus vector.
You put input 3.
I put input 3 in there as since I had a scalar here. We'll say that we have a VDB activate, and I'll just pull it here and just say that this third input is vel. Essentially, I didn't build it. I just
got it.
Set it. It's probably it makes more sense if I actually build it. So here's a vector field coming into input 3, and now I'm going to read that vector field, and then this one's reading my scalar field. So sorry for the confusion on that.
No, that's great. Thank you.
I'll leave those in there just as references. Save the file. So okay, great. So that answered your question. Awesome. Let's see. So there's that. Next demo. Let's see what we got here. Oh yes, this one. Sorry, I've done so much, I'm like forgetting half of the stuff I built. So masking. When we were talking about earlier, we talked about those, remind me of the name, leaf nodes. There we go. The leaf was causing glitching, that popping. And I'll illustrate this really quick with, I have a lot of visualizers in here, so you're more than welcome to use those. In this case, I'm gonna use active. And I'm on, make sure I'm on everything correctly. Cool. So this is just a generic box with points from volume, nothing fancy. I put a rest on there just for a process I did later, I think, but it's just a box of points. The primary thing is that I'm basically wanting to advect points. I'll actually turn the visualizer off for a second, and we can see how these points are shifting. This is a live sim, mind you, so it is running a little slow. I have it low res. So if I do it like this, we can see I'm advecting. I'm doing this based on a pyro sim. So all of this is a grid, scattered points, made some density and temperature, and then volume rasterized it to then make a pyro sim. And that pyro sim is outputting density and velocity. And I am also, in one note on that, we get into pyro solver later as well, but I'll point it out here since it's up. When I talked about various sims outputting VDB versus volumes, standard volumes, the field that we get here, the velocity field, is by default a native Houdini volume. So we want to convert it to VDB. And as another efficiency thing, we want to make it 16-bit, just so it holds a little less information. It keeps it lightweight. We still retain the majority of the movement, so it's not that big of an impact outside of storage space and memory. So that is basically going in and doing our simulation to create basically just a simple pyro sim. That's all it really is. That is being used, and I'm doing my own advection within a solver, I believe. Down here, if you want to check it out, I'm advecting the points and whatnot to do that. I'm not really going to go over that because it's more about this got you that we run into. And it was basically the popping. As I step through this frame by frame, the first frame we see square. We see another square. We see all of these other squares. Those are the leaf nodes getting activated as the velocity enters those zones. And this is what causes the popping, depending on how you're applying your velocity field. If you're doing it for advection, if you're doing it for some other instance, I can't think of one off the top of my head, but regardless of how you're using it, those values become activated. Why is that? Well, the leaf nodes for one, but considering we had a sim that's shaped like this, why would our velocity be blocky? Well, that has to do with how the velocity gets output. So let me make sure, yep, it's going to be this one. This is what we're getting. This is our velocity field. As each leaf node gets activated here, the velocity fills that. The voxels that get activated in each leaf are wholesale. It's all filled regardless. So you don't get the shaping of your density. So we get this blocky source. This is why we're getting blocky glitching that's coming across the board. And if I look at the volume trails of that, we can see how that's activating and how the movement is happening right here. So we're seeing that twisting and curling even subtly on those activation locations. We don't want that. This is causing us issues. You know, we're being efficient, certainly with VDB, but it's causing other headaches. And a lot of it probably has to do with the conversion of standard Houdini volumes, which are grid domain based. So therefore, all of those voxels exist in the Pyro solver. And converting the VDB cleans up, but not in the way that we would kind of expect, because there's still information there for them, for the sim to handle. So I'm going to show different methods. The initial method is no mask, which is why we're seeing the blocking. So I want to show you another method that takes it to here. And this is basically, and let's get our fix the font nodes, make sure we get velocity trails in there. The difference between that, we're basically cropping out all of that bad information as best as possible and keeping all of the motion information. And if I go to the other setup here, we go from blocky voxels to only the voxels we need. Now, this is still not one-to-one to the density, but it's definitely a lot better than what we had before. What this is doing in this particular case, and this is method one. So method one and the mask method, I've tried to name these so they correlate to make it easy to find, since I have a spaghetti bowl of nodes in here, is that we are taking our velocity, the output from the sim, which is invisible by default. That's Pyro solver does this as invisible. You can visualize it as smoke, but it's kind of pointless because negative values can't be visualized, unfortunately. So keep it as invisible anyway, just to keep things lightweight. I just used the split is why this is separate. I'm taking density and velocity, splitting it by saying, give me velocity. So I now have velocity here, and I now have density over here. So what I'm doing is taking a VDB clip. So this is a built-in way to mask a VDB. So we can take a group, in this case, our velocity. You have to do the expression, which is kind of annoying, or just click here and it'll do it for you. At name equals velocity. And that is because this is the name of that primitive. So velocity, in this case, you don't necessarily have to put that there because there was only one, but out of habit, you just want to kind of make sure you're being explicit about what you're doing. So put that there. Clip 2 is set to mask VDB. What are we going to mask by? We're going to mask by this field right here, which is called density. And that's going to be inside our second input, mask VDB. And that comes up to here, which is VDB activate that I have connected to this VDB. Why do I have that? I'm creating a buffer. Here's another tab of VDB activate. It's expand. So let's go to my visualizer setup here, because this is easier to see this way. And actually, I'll take it to like one of these. So this is our mask, our density that's happening right here. And we're saying take our density and then expand it. And we can expand it by voxels. So I have 4 in this case, but we can see how we're taking the information and it's exact if there's no expansion and then pushing it out. Why am I doing that? So in this case, I'll take it back to 4. And let's get back to the actual output here. For this method, go back, play it through. And now we'll see there's no blockiness. We are going to see some other issues. Now, I will preface that this is not bulletproof. All of these methods are not bulletproof. And it's going to be based on your scenario. But in this particular case, the advection prominently kind of contains it. We are going to get outliers like these particles down here that escape and just stop. These are going to be things that you'll have to handle Individually, you can, call particles if need be. You can try another expansion. I have two other methods in here that are variances of this that help, but again, are not bulletproof. They're not going to be 100%, but they are way better than dealing with that, where you have all of this extra noise that's popping in there. So this is just alternative methods that we're going to be going through. So let me get this out a little bit further. So that is one mask method, and that's just basically masking with density. Make sure I'm on my output. Good. So the other method here is this method, right? Yeah, method 2, where I'm expanding, and we can see the difference between the two. I'll zoom it in and make it a little easier to see. It's slightly more expanded out. The difference in this setup is I'm expanding again. I chose in this case to use by distance instead of specific voxels. You can do it wholesale or just by distance. So I can do it by this to kind of bleed it out further and further. And then I smoothed it. So I am, give me 1 second. Grab a quick drink. So what I'm doing is smoothing it. And what this is going to do is take kind of that harsher edge of the expansion and kind of blend it out a little bit more, kind of give us a gradient of sorts. Unfortunately, I don't have a fog visualizer for this up, but it's basically going to expand out to this section over here. What I can do is just activate it this way so we can see it directly. So I expanded, so source, expanding to give us buffer, and the expansion is specifically, so when I smooth it, I don't clip, essentially. We want to activate voxels so we have room to blend out for the smooth. That's the primary reason for the expansion. So we can see how that kind of smooths out. Unfortunately, this is a global smoothing, so you do smooth out any details. So that's one of the cons to this method. You can change the operation just to kind of mess around with some variances of it to kind of mitigate that a little bit. But again, not bulletproof, but we're trying to work as best as we can with the limitations that we have. So it's just a simple filter. You can set how many radius voxel to blur, and then the iterations for it to calculate. So you can kind of like fine tune with the iterations. From that, I get into Vex. So let me pop this back real quick. And actually, I'll leave it on this. So we see, do we see it? Oh, no, because it's invisible. So let's keep it on this. I'm going to hit Alt-E in this to pop it out, just so we can see this, and Control+ to zoom it in, so we can scale up the text and make it readable. So this is a volume wrangle. What I am currently doing is taking our, let me move this over a little bit so I can see the exact route that we are taking. Give us some space here. So I'm taking our velocity, piping that into the first input. I'm taking our mask, piping that into the second input. So that's our scalar that we're doing. So that's traveling this direction. So what I'm creating code-wise is the volume sample function. And there's a number of these functions with Houdini 20, like I was saying, has a bunch of new ones. If I say volume sample, you'll see volume sample I for integer. P, I believe, is vector 4, which is like orient and quaternion stuff. Volume sample U, I want to say, is matrix. I haven't messed with this one yet. I'm pretty sure U is what they're using for matrix. The volume sample V is the one that we were using in VOPS. That's our vector. So volume sample is scalar. It's not showing in the list because I've already completed the name itself. If I kick it back one letter, you'll see volume sample in there as well. So volume sample is the scalar version. Volume sample V is the vector version. So what I want to do is sample those values from the voxels like I did with VOPS. So this is the Vex way to do it. We basically create a variable, float variable. We have to define that. And I'm just calling it D as a simplicity thing because it's density. And we use volume sample, and it requires 3 arguments. And if I get rid of the parentheses, we can bring up the help for this. And it basically says it does a float, and there's 2 usages that we can do. We need the geometry. This is basically our input geometry. So that's going to be our 0 input, 1, 2, and 3. So I'm saying 1 because I want my density. I want to sample that. And we need our int prime or string volume name. So there's 2 methods, just like the VOPs. We can use numbers or we can use the name. Again, I like to be explicit, so I'm using the name. It needs to be a string. So it's double quotes and density. The last part of it is the sample position. Just like the VOP setup, we're looking for a vector position. So we just say v at p, which is the native position attribute for the voxels and for points and for primitives and so forth. So that one carries across the board, thankfully, for voxels, makes it nice and easy. That gets our information from the density field. Over here, I'm doing a little bit of a tweak to the information. And I don't want to change that before, make sure it stays D. I'm saying take our variable that we just created. We have values in there. Take that, and we're going to reassign it. And we're going to reassign it based on this little equation. This is what's known as a inline if statement. So if you're doing code before, if a condition, I'll just say condition, else, do something else. So you would execute something here. You'd be like, do something or do something else. So you have 2 options, option A to option B, based off of whatever this condition does. And it's not with an N condition. So this is a similar version. So the condition is here. This is kind of a pseudo replacement to say that we're done with the condition, but we're doing the brackets of sorts without doing brackets. So it's a question mark. And then we're saying use this value, else use this value. So the colon is the kind of replacement for else. So this is our do something else is what that's referring to. So I'm just saying, take the values that we have. If any of those values are greater than 0, make the actual value 1. If it's not, make it 0. The reasoning for that, if I'm going to mask by density, we get into the math equation that we talked about earlier, the gradient of our density, because our density simulation has thick and thin parts. So mathematically, I would say, give me the full value of velocity here, give me the 0.01 value of velocity here, because my density is dissipating. We didn't want that. I want an actual mask. I want the voxels here that are all set to 1. And that's essentially what I'm doing. I'm pushing this all to a single global value. And once I have that, then I can say, let's set the velocity value. So that would be on the volume wrangle here. So we have our velocity coming in, sorry, here. We're just going to directly set that value on our wrangle. And that's what that is. It's a vector data type. We're using the attribute. Thankfully, it's the attribute format to read these fields, even though they're a primitive name. Technically, it's a primitive attribute for the name itself, but this translates in a volume wrangle. It gets translated for us, thankfully. So we can treat it as an attribute. We just say v at vel, and we're going to say take the existing vel coming in and times equals our density. Times equal is just shorthand for saying assign this v at vel times our density. So instead of typing this twice, we're just doing a shorthand saying times equals. Hit apply, accept, and that gives us that final velocity. Once we have 0 values, because we did define 0 in there to kind of mitigate the voxel values, we want to clean it up. We want to deactivate those voxels with the V2B activate set to deactivate. So that cleans it all up, and that's what gives us that final mask. Again, it's invisible. So let's go to the output, and that's what gives us that masking option on method 2, like so. So you can see that this is slightly further out than doing density straight up with the VDB clip method. So we get to smooth it and have a few extra voxels in there and kind of mitigate some of the values. The result of that, I'll just kind of give you the quick, there we go. Pull it back. We still get some strays here and there, like it's inevitable, it's going to happen. But this gives you a smoother kind of fall off on that outer exterior versus the sharper kind of edge of just doing the VDB clip method. So one last method for this is taking, and we talked about this. I'm gonna go to my trails here and let this play to show our velocity trails in this. We talked about this in the first class with magnitude. We're talking about the length of a vector, and that gives us basically speed. Magnitude is speed of the vector value that we get. So let's put that illustration out there. We have the vector. The length of this vector is whatever it's going to be. We'll say 10. This is the magnitude of that, also known as speed. And this is just a general mathematical equation. You have X, Y, and Z. It's a vector. Well, our velocity, even in a field form, is a vector. It's still, we can simply still do the same mathematical equation. There is a node which is really awesome called VDB analysis. This node basically gives us a bunch of operations in here. We give it a group saying what field we want it to run on. We just want it to run on our velocity field, which is actually, it's hard to see the line. It's going all the way over here to our velocity. So I'm connecting to that. That's going in. And I'm creating what's called a mask field, which is why it says mask here. And that's just a name. It can be anything you want. I'm just naming it mask so I know exactly what it is, being explicit with it. So I'm saying use our velocity, and the operation, I want to use length. There's a bunch of stuff. You can get the gradients, the curvature, Laplacian, closest point, divergence, curl, normalize, all of these different operations of a volumetric field. But we want the length. We want that vector, and it converts it to a scalar for us, the attribute value. We won't be able to see the value directly. If I recall, yeah, exactly, because we're still in a field form. We would have to do the VDB slice to see the active value for the voxel. But I'm getting that value, which would be the magnitude speed. But in this case, I just want it as a value that I'm just going to make it as a mask. So I'm defining our mask off of the velocity directly. I'm not using density in this case. So I'm going to take that and I'm going to remap it. So let me get my output here. And essentially what this is doing, I'll kind of pull this, if I recall correctly, if it's, oh yeah, that's right. I always make this mistake. I actually did it here. I have the main controller expressioned over to my controller here. So this is why that wasn't updating. So as I change my curve, I can start eroding into that velocity field or expanding it. And I can change this to any of the different, curve types. It's B-spline at the moment that we have. And this allows me to kind of remap the velocity data as a new type of field based on its magnitude. So we're getting that length of it. And the max length in this case, I'll pop this out so we can read the whole thing. I'm creating a variable called floats, or is a float called fit mask. And we're going to take that mask coming in, so this mask field, and we're going to fit that. We're going to remap it. We're going to say fit it from 0 to whatever its max value is. I'm defining that as a value of 20. You can adjust that accordingly and remap that range to 0 to 1. So this normalizes our mask. What that does is it allows me to take the mask value, which is our main input, And again, times equals, we're going to multiply that against another ramp that's based off of our fitted remapped value. And it's just called remap underscore map. So that is what gives me this. And we just basically multiply that to alter the mask itself before we then deactivate, again, voxels based on 0. And then we throw it into a VDB clip. And we're saying take our velocity, mask VDB it, and mask it by our mask. And that's how we end up cropping this a little more specifically. Now, the difference is, oops, we hit H on this. I think I hit a button somewhere that threw things off. Did I cut something off of here? Oh, yes, I changed that. Every time I hit my hotkeys, let's undo, undo, undo. There we go. Make sure I'm on my main output and let that run for a second. So masking via the velocity directly, just in a kind of remapped form, turn this around this way, gives us a slightly different shape. Let's see here. If I go to the different methods, we can see how those shaping kind of changes. These two are density based. This is velocity. So if I go to this form, we can see how the voxels shift accordingly. So we are getting more exact kind of mapping to the overall mask in this particular case based on the velocity values. And I'll pop it back to the beginning here just to show the particles part of it. And we can see how this runs. Now you can see some of the popping coming in, and that's where we can start dialing in the actual curve to kind of choke it in a little bit. So we have a bit more of a refining control in this particular case across all of that. So yeah, that's that particular section for masking. Any questions on this section?
Looks like we are good.
Awesome. The next section is really, really easy. So we're going to hop over to this one. And we're going to talk about the camera frustum. Pardon me. So I have a couple of different examples in here. There's a volume source, a SDF, and then I have the actual simulation in here to show how we can crop even an actual volumetric simulation. So what I want to do is actually exit this and hop up top because we need the camera right now. So selecting the camera, I'm going to make it active so we can actually see the camera. This has been a thing that's bugged me for a long time, and a lot of users, I've seen it posted everywhere, including myself asking about it. Where's the camera frustum? We want to know where our camera view is. Where do we see our field of view? How do we know what's in frame? And this is something that definitely, in my personal opinion, could be way more simpler as far as having it displayed. But it does exist. It absolutely does exist. You don't have to use a VDB. You don't have to do some crazy vex, make polylines or whatnot. Select your camera. And I have the step-by-step right here. Hit enter. You're going to be presented with one particular view. If I right click anywhere on the actual handles, you want to make sure it's highlighted. If you go outside, you won't get the right menu. So you want to right click on that. Come on. There we go. You'll get a contextual menu. The options in here are orientation handle, which is the default. That's what we're looking at right now. There is a focus handle, which is Z. So that gives us this kind of look. There is one last one called frustum. Right, where'd you go? Up here. Frustum handle, F. So all we have to do is click F, just like that, and we get our frustum. We also get our focal length as I select things. If I select here and go to here, you'll see things update. So we can do the far clipping. We can grab this and do, I believe that is, one of those is focal. I forget which one. I want to say this is the focal one, but it's not showing that actual value changing at the moment. But this gives us our frustum. This is exactly what we want. So we can now hit escape. And now what? Well, we have to hit enter every time to see this. That's a pain. Right click. Let's try it again. Come on. Right click. Persistent. This, now when I hit escape, will now keep our frustum there. It will always be there. Sadly, when you turn off the camera, it still will always be there. So when you say persistent, it means it. It will persist. So for right now, we just want this setup. We want the camera turned on and we want the frustum turned on. And then we can dive right back into our field. And you are very welcome, Chad. I'm seeing the chat notice on there. Everybody's complained about this, including myself. So now we can see the literal action that's happening here. That's our frustum. That's what's actually cropping. We are doing this with simply the VDB clip. So these are just the different sources. So they're just the VDB, the SDF, and then the volume sim. The VDB clip is just grabbing the source on the first input. And all we're doing is saying keep inside. If I unclick that, it inverts it essentially. So if you want that for any reason, you get that. But just change it from mass VDB to camera, just like that. And then point to the camera. You can type it in, or you can just click here and select your camera right there. You can change padding, which is really, really awesome. If I go to 4, or well, I'm not really square on the thing. I'll keep it on perspective and kind of maneuver it like so. But you can do padding. So if I crank this up, you can say, take the frustum, crop it, but give me a little extra. The reasoning for that, if I select my camera and look, we have this buffer now up top. And if you're rendering, sometimes you may need shadows casting. So maybe you don't want this to literally be cropped exactly to the voxel, because you may get some weird lighting blips depending on how it's being, cropped out here. So you have the option for X, Y, and Z. So you can do it in all directions to kind of give it some extra space. So if I lock this, and we can see as I move around, it's going to crop out anything within that field of view. I don't have the text as part of it, but the field itself will actually get cropped. And the same goes for SDF. You can use it for that. And for the volumetric simulation, if I play it, we can move that around. And this is all live simulation. I didn't even bother to cache this. It's so low res. But so that is masking via camera frustum, and how they actually even get the frustum for that matter. So that puts us at 2:42 right now, time-wise. I don't know how everybody feels. We can definitely.
I think we're at a good spot to conclude.
We can definitely carry
today.
this.
Yeah.
Yeah, I don't mind at all carrying this over. I do have some buffer room in the other sessions, so it's not like we're going to overstack everything. I'm not going to do a 4th session unless you really want me to. But so
any last
we can
questions
next session
with what we've covered so far today? Anybody?
Yeah, any questions, comments, concerns, suggestions?
No, just a comment. No, it's good to kind of see some of the stuck particles thing has always been a real pain.
Yes.
To maybe understand. I mean, because you can, if you're using the with the pop effect by volumes, it seems like I get a lot of stuck particles with that. No,
Yeah.
you wouldn't just rebuild it. You can kind of take it apart, just build a simplified thing, and add just velocity to the dead particles. But it's good to know where maybe the problem's coming from, and I wasn't
exactly
aware that it was related to the leaf nodes and that the popping there.
Yeah, the efficiency and optimization is like helping and hurting us all at the same time. It's really crazy. The other thing, I'll point it out really quick because it does relate to that question there about that slowdown. So you're in AdopNet or even any of the other sims. Come on, dive in. There you go. And you're using that pop effect by volumes, which we are going to be using a lot. We did before, we're doing it now, and we'll expand upon that. But one thing, and I even answered this on Reddit recently, the default is set to update force, treat as wind, and the key thing here, error resistance. This is what is actually screwing everything up. You can turn treat as wind off, and you will get where, say your smoke is like this, your particle ends up out here, and it immediately does this like super slow, creepy crawl. If you have gravity, then it's like thunk, and then it just does one of these like drops kind of a thing. That's what's causing it, is air resistance. What's happening is your velocity is no longer touching and affecting that particular particle. And the only thing left is this air resistance, which is basically a drag force. So now it's out in the middle of space with gravity only if you have that on. So it's basically just restricting it from moving at a respectable speed. If you turn that off, that will basically, if a particle exits, it'll maintain its velocity and then decay depending on what other forces you have. That's kind of the easiest way. Plus, you can also flip it to the other modes that are in there. But that's the number one reason for why particles exit and they stop, is because of that.
Yeah. Okay. Cool.
We have another question about SDF and mesh grids.
Okay.
One second. Can the mesh grid plane be converted to SDF for pyro and flip collisions?
The SDF.
Chad, if you want to ask your question, maybe.
Yeah,
it
just a
could.
little more clarity, because SDF will be used for collisions, definitely.
Yeah, right.
Because
Sure, I just wanted to.
Oh, sorry.
I just wanted to. Yeah, so if I drop down a planar patch or mesh grid, and convert that to a VDB in efforts to work as a collider for flips or pyro, is that going to work because it's a plane, or do I have to always use a box or an actual piece of geo?
Yes, you're going to need thickness to it.
Yeah.
The collision primarily is defined by like normals and the surface. So the surface by itself is only half of the equation. The normals tells the system which end is out and which one is, which side is in and which side is out, kind of a thing. So if you only have a plane, it gets really confused and it has no idea how to treat that. So it does need to have thickness. So if you use a plane, you can throw down like a poly extrude and give it something that is thicker than the particle separation or the voxel size that you're using. Because if it does go too small, then again, it'll get missed by the solver because of the substeps that you have. If the speed's moving too fast on a particle or something, it may miss the collateral, completely if it overshoots. If the particle is here, this is your collider and it's super thin, and the calculation says, oh, I need to move 2 units, which would put me here, it may not see the collider because it's now looking at here, unless you have like, or a ton of substeps for it to catch it in the middle. Awesome. Yeah, poly extrude is the fix for a lot of things.
Awesome.
Cool.
Any other questions, anyone? I think we're good.
Awesome. So yeah, we'll go over these 4 in the next session. They're not too bad. Again, we're going to focus mostly on the yellow sections there, but we are definitely on that long side right now. So thank you for sticking it out for that.
Yeah, thanks everybody.
Stop this so we can see each other now. Yeah, thank you for holding out for the 2-week delay. I apologize for that, and sticking it out even for the long class. I'm going to give you so much information, you're not going to know what to do with it, but it's a lot of replay value.
Thank you so much, David, and feel better soon, okay?
I'm already feeling better. It's the stupid cough just keeps bugging me.
Yeah, I understand.
Yeah.
Have a great weekend, everybody, and we'll see you next week, okay?
See you next Saturday.